Good morning! Welcome to another fun-packed episode of MakerPnP videos about pick-and-place machines. Alright then, who am I and what are we doing? Well, we've got a pick-and-place machine behind us here. This thing. And as you can see, it's got a hole in the front. The reason it's got a hole in the front is because I was decidedly unhappy with the original software that was on that machine, and I was also unhappy with the replacement software that people said was good. So we're building our own software. However, we could put our own software on the control board that's in there. You could, but the problem is I've only got two of them. One of them is running at PnP, and one of them has the original software, and I don't really want to upset either of those boards and keep yanking them out and changing them out between the machine and so on. Let me just grab the control board. It's on the desk over here. This is said control board that I purchased at the same time as the machine. So we need to basically make a new version of this which does all the same things and lets me plug all the wires that are in that machine into a new version of this, but design it from a new software, MakerPnP, so that we can run our own software on a MCU or other things. And have it do all the things that I want to do in a way that's more kind of 2026, you know? So, that's the plan. So, where do we start with this? Well, yes, I'll show you where we started. Here we go. Right, so there is a link to this photo album here. So we've got a bunch of photos. Let me copy the link for that one. There we go. Let me just pop that in the chat. There's the chat if you want to look at these photos. So there's a whole bunch of photos of what was in the machine at the time that I received it. Yeah. So there's loads of wires. So it had this. It had all this inside it. This is basically a touchscreen computer. And that's in addition to the control board. So the control board does motor control and things like that, and reading sense and so on. And then there's another board which actually runs the main sort of like planning software. And we have a similar approach in MakerPnP software. That's the idea. So it's got two boards in there, some fans, some cameras, some vacuum pumps, some power supplies. What else have we got in here? We've got stepper motor drivers with stepper motor drivers over here. There's two of those. Fans, another fan. This fan was bad at the time that I received it. It was terrible. Put my own fans in there instead. Some old PC fans. Yeah. And then it's got cameras as well. One on the head, one inside, and this is how the old software used to look like and work. And then it got fitted with PnP, and then there was a process of doing that. So there's a whole bunch of photos in there. I also made up a new light ring circuit board for it to go around the light over here, and fitted new cameras, and this is how it's going to look in the future with a Raspberry Pi 5 and a global shutter camera for the main cameras. I think I've talked about that in one of the other episodes. And then on the back of the head, on the head rather, there's three small little circuit boards. There's one which controls a solenoid for a drag pin feeder. There's another circuit board which controls some vacuum sensors and some vacuum switches. And yeah, so that's kind of like the scope of things. So, in order to understand what it is that we need to have to make the machine work, you need to understand what's in the machine to start with. So, I reverse engineered the schematic of the existing board. So over the last few days, I've been going in and getting the scope probes and finding out where everything goes. Big shout out to Matt the Baker from the Discord server, who years ago ported SmoothieWare to this board, and that's how people run OpenPnP. And as part of the process of doing that, he basically created a nice Excel spreadsheet with a whole bunch of information in it, which I have updated as part of this process. Where's the files? I'll show you that file. Spark file, this one, resize that, there. So there's basically a big list of pins for the original processor and their functions, which is taken from the datasheet. And then this was updated with how they are mapped out to how the machine uses those pins. And a couple of very handy little photos were created at that time. So a photo of the top of the board, bottom of the board was created, thus. A photo of the other side of the board was created, thus. And a photo of the MCU was taken from the datasheet, and this was then all overlaid and transparencied and lined up so that you could sort of see through the board, which helps with reverse engineering and cross-referencing things. It's not 100% accurate because if there's a component in the way, you can't see where the traces go, like on the top layer, for instance. So it can still be a little bit tricky to work it out, but with the aid of a multimeter, you can get most of it done. And as you see on this board, there's many unpopulated things. Let me go back to this one. There's many unpopulated things, and I reverse engineered those too. Had guesses at them. I think my guesses are pretty good. We shall see. But to be honest, it doesn't really matter because if they're unpopulated, then I don't currently need them in the machine anyway. But yeah, I did it because, you know. So we've got this board. Let's sort of have a look around the board and talk about the things that are on it and look at the schematic. So it all starts with power, right? So down here on the bottom left, we've got power section. There's basically 24 volts in and 24 volts out, and that goes to a earth connector, which is down here on the bottom left, and that earth connector is also going to the PE pads up here on 6 of these connectors. Then it has a 7-volt regulator. It's an adjustable regulator, but it's set up for 7 volts. Then it has some input caps, output caps, and the inductor for that. And then it's got some ESD protection, diodes for the regulator, and then it's got 3 LDOs. 2 of these LDOs are for 5 volts, so it's got 2 main 5-volt rails, and then it's got 1 main 3.3-volt rail. And then it's got this unpopulated little module here, which looks like it's some kind of perhaps transformer, I don't know, or filter or something. It seems a little bit weird. It's probably a filter, I'm guessing at this. I don't know what that is. Because on the other side of it here, there's another LDO, there's a socket for another LDO over here. So yeah, it takes the output here, the 7-volt output goes through here, goes through another LDO, and then it says 5 volts here. So I don't know what this is. It's probably some filter, who knows. And this is for an RS422 circuit, which is digitally isolated from the MCU. Let's have a look at that in the schematic. So we go into power. So this is the regulator circuit, and where it's not interesting, I've left a couple of things out, like on, off, and feedback. You know, I could buzz these things out, but we're probably not going to be using the same regulator in a new board. So yeah, it's not particularly interesting. So that's the earth. We've got the main regulator, and then we've got the 3 other LDOs here we mentioned. So then we had the RS422, which is 2 lots of RS485. That's how it's made up. And then you can see the optical isolator somewhere here. Yeah, here it is. So we've got all that. So we've got some optically isolated I/O. Then next to that we've got CAN output, which is probably one of these chips. Not that one. This one. Probably one of these. You know, when you reverse engineering things, you've got to look at the date codes, because the date codes gives you an idea of what was available at the time that they made the circuit board. And if you've got a circuit board and it's made in 2018, and then you've got a CAN transceiver that's made in 2020, it's not going to be that CAN transceiver. So you can discount a lot of more recent things by checking the date codes. Yeah. So we've got CAN, then we've got some analog inputs. Analog inputs, which are these ones, and these basically wire straight up to the MCU. Then it's got some digital inputs. It's got 8 of those with ESD protection on those. I'll come back to what things are used for in a little bit, but let's just carry on walking around the board. Then we've got some, where are they? Down here on the bottom right. Hold on a second. You can't see it, it's behind my head. Down here on the bottom right. Actually, let's do like a split thing. This might be a little bit better. Let's see. Let's arrange things a little bit. Yeah, there we go. Yeah. Okay, now we can look at both things at the same time. So down the bottom on the right down here, which is still behind my head, there's, and this is taken from a different machine, these photos. My machine doesn't have that connector. That's used for like a USB camera switcher. Because the cameras are analog and it has one capture card, and then it basically switches the input, the analog input, to the capture card from one of 2 cameras on this machine. So those inputs are these. So there's 2 optocoupled inputs and 2 optocoupled outputs. Let's move this up a little bit away from my head. There we go. So over here you can see that there's 1 populated, and then these 2 here are probably the same as this one, but in the other orientation. So when you're designing a PCB, you don't normally have like more components than you need, and you try and reuse the same ones out of your bill of materials. So it's probable that those unpopulated ones are the same encoder, same isolator rather. I don't know, but they probably are. Yeah, okay, then what? Then down here on the original photographer's machine, there's 2 connectors. Mine's got different connectors. Mine's got this one populated, this one's not populated, and then this one's populated. And mine's got a chip populated here and not here. So with my machine, it's got that touchscreen control board, and then this RS422 is wired to that touchscreen control board. On the machine that this came from, you plug it into a separate dedicated PC, and therefore it has connectors on the machine to allow you to do that, and these are used for that. So on the schematic, that's like this. So it has one of those for this, and then it's got these two, which are these ones over here, and then it's got this chip which goes to this connector over here. So that's what that looks like. Then moving around the PCB, we've got these ribbon cable connectors. These disappear off to the driver boards like this. There's a ribbon cable here. Have I got a better photo? Let's have a look. Yeah, here we are. That one. So it's got these ribbon cables over here. They disappear off to the stepper motor drivers in here. So that's where they go. Those connectors are these two connectors here, which have a bunch of enable signals on. And they go into these chips next to them to isolate the signals. And there's a signal to enable this chip and disable the chip as well. Additionally, my machine has this connector up here populated, and that goes off to a feeder. So on my machine there's two feeders. There's one on the left and there's one on the right, and it's basically just a stepper motor which moves, peels the tape back, so they're called peelers. They don't actually feed. They're not really feeders. They're more peelers rather than feeders, I suppose. Because all they do is peel the tape off. And it attempts to peel the tape off everything that's in the machine on the rack of component reels that are in there. But if there's too much tension on it, they basically slip, so it doesn't end up pulling the tape off all of them. Just the one that was fed through a little bit. Moving on, we've got a 2-pin connector here for emergency stop. Then we've got a bunch of chips and a bunch of connectors up here. So there's 5 of these chips, the signals of which are distributed over 6 connectors. And then one of the chips, this one, has 2 of its inputs disabled, basically. So it doesn't use 2 of the channels on this, which is why the amount of pins on here divides by like 4.5 or something. So it's like 4.5 chips. So there's 6 signals per socket. And these signals are for the encoder inputs. So on the back of the X and Y motors on the machine, let's see if I've got a photo of those. I'm not sure I do. Yeah. So on the back of this motor over here and this motor over here, there is an encoder, and it gives you a differential output. So what these chips are differential line drivers. So it basically takes the high voltage and the low voltage of the differential signal and then combines it into a single signal, which is then fed to the MCU. And those are these on the schematic. And then this is that chip that's in the middle that's got 2 of its inputs unused, which you can see here. I should probably mark those as not connected. There we go, fixed. All right, next. We're nearly there. So then next up, we've got all this stuff up here. So what we're looking at here is 6 outputs which take a second 24-volt input rail, which is not connected to the primary rail, and then these are driven through this U10 chip over here. They are driven through this, so there's this output enable, and you can send a PWM signal through this output enable signal and it ends up on the other side of it, but isolated. Is it isolated? No, it's not isolated, it's just level shifted, I think. Yeah, that's what these are. So, basically these are double MOSFETs, these chips here, and there's basically varistors and diodes on the outside of those to connect up to these outputs. Yeah. And then there's another one of these here which is unpopulated, but it's likely the same as one of these because the circuit is the same. But it's connected to different. It's connected to the MCU differently, which I'll get onto. So 6 outputs, and those outputs are used for things like driving lights. There's 2 lights in the machine. There's one on the camera, the bottom camera, and there's one called a work light. There's also a drag pin solenoid, and oh yeah, the vacuum switches. So it's used to drive those. Then we've got 2 more 24-volt connectors next to the other 24-volt input over here. Those are driven by these 2 MOSFETs over here, and then this circuit here. These 2 circuits here are identical, driven by this chip over here. This unpopulated one here goes to this other one that's up in the corner, so it drives 2 more signals over here. These ones are the isolated ones. You can tell they're isolated because the ground plane is not the same. You know, it's not present on the isolated ones, whereas it is on the non-isolated ones. So these are isolated. These 2 chips are probably identical because they've got the same sort of outputs and so on. This is basically just MOSFET driver circuit. But these MOSFETs are supplied by their own 2 LDOs over here, which are these over here. So there's one which takes a 12 volt, so it takes the second 24-volt input rail, goes down to 12 volts, and then goes down again to 5 volts. And those outputs are then used to drive the rest of the signals. So these MOSFETs use the 12-volt outputs, yeah, and then the other side of things are used for the 5 volts. And that is here. That's what that is. So, yeah, that's basically it. That's basically it. So, yeah. So that's an overview of the existing control board. So we basically need to make something that does all these things, but also allows me to run better, newer software in the future. So, what next? So now we have an understanding of what this is doing. Well, what the outputs are really. we've got an MCU and it's wired up to all the chips that control the outputs. There's not really much more to it than that. However, it's the way that they wired this chip up. Well, it's not the way I would have done it, let's put it like that. So they used an STM32F407 for this, and yeah, let me bring up a file. I'll show you what I mean. So in the process of reverse engineering this, I used the STM_CubeMX tool to create a CubeMX pin layout for the MCU. Come on. There it is. So, yeah. So for example, when I say it's not done the way I would have done it, let's just look at these 6 output pins. So there's a couple of issues with this. Well, more than a couple of issues with this. The way that they did it, they were just went, oh yeah, there's 6 pins next to each other. They'll do. No, they won't do. Not at all. So we've got 2 on GPIO-D, PD 14 and 15, and then we've got 4 more on PG 2, 3, 4, and 5. And if we look at the pin functions that are available on this, we've got a solenoid output, and it's got a timer channel on it. So, yay, great. Now remember that the circuits for each of these are identical. And this one has got a timer channel on it, so fine, great. This one, no timer. So you can't create a PWM signal on it. But you've got circuits that are the same. So 2 of them can be PWM driven. What about the other ones? No. Like, why would you put 6 equivalent circuits, these ones, 2 of them on PWM and 2 of them not on PWM? I don't know. Let's look at other things that this chip can do. Encoders. So STM32 processors. Where are we? STM32 processors have peripherals in them. Here we go. Let's bring this up. Give me a moment. Too many windows. No. This one. There we go. Okay. So they got peripherals. Processors have got peripherals. There should be a. Where's the diagram? That's what I'm looking for. Right. We've got peripherals. These are all the different peripherals that you've got in this particular processor that they used. And there's timers. Right? And if we were to look at the timers, finding things in these is not always easy. Timers. Oh, I need to look at the reference manual. Okay. Reference manual. There we go. Okay, reference manual. That's better. General purpose timers. And then inside these you have block diagrams of the peripherals and what they can do. And that's what they can do. Encoder interfaces. Okay. So if you feed input signals to this timer, it can basically go, oh, is one edge leading the other edge of the 2 encoder outputs, right? Because that's probably how they work. It's got they all seem to have like a two outputs on these encoders. So let's see if they use those. Place your bets. So we've got encoder outputs. So if we start from the connector, we've got the connector. We've got the encoders, which go to these. And then they go over to these. Right, so we've got EDC nets over here. Right, if we look at the EDC nets, EDCA plus, for instance, which goes to U22 1A and J4TP3, which then goes to the MCU over here on PA15, for example. It's just random one. QMX, PA15, flashing away up here. Ooh, this one's actually supports it. Interesting. PB1. Let's have a look at another one. I haven't actually gone through and see whether all of these do. Ooh, this one's actually got it as well. Maybe they do use the encoder inputs after all. But wait a second. EDZ. PB5. Let's have a look at another one. I'm curious now. Hadn't actually looked at this. PB5. Find it this way. There it is. Oh, maybe they do. Okay. They got that right, I think. So you can use the encoder outputs on hardware timers. But it's important to know that that is what's required for processing all these signals. So, moving back to the schematic. Yeah. There's lots of things on this that I'm not overly happy about, like the arrangement of pins to peripherals. It's not well thought out. So, okay, so yeah, there are other considerations as well with this, like voltage tolerances. So some of the pins, like these ones down here, might be connected up to 5 volt peripherals. That seems quite common on this machine. And if they are, then that means that the MCU needs to have 5 volt tolerant pins on these. So let's just have a quick look at this while we're here. So those pins were on AIN1 and they were up here. Other weird things going on here, look. So it's so strange. Like we've got PA4, 5 and 6 up here. And then we've got another analog input on PC0 down here. Like, why wouldn't you just use the same GPIO port and 4 consecutive pins for these things? I don't know. What's special about something else? You know, why didn't they use PA2? It's kind of weird. You know, or rearrange these two. Yeah, I could dig into it more, but PA2, look, so that's down here. So these are not used. So we've got analog inputs, PA4, 5 and 6, datasheet time. So on the datasheet, it has a list of where everything is, and it's got this I/O structure. So if something is 5-volt tolerant or not. So it needs to have FT. If it is, say, 5-volt tolerant on PA0. And we were interested in PA4, 5 and 6. Let's have a quick look. So PA4, yeah. Which is not 5-volt tolerant. Interesting. So PA4 and 5 are not 5-volt tolerant. PA6 is 5-volt tolerant. What about analog input 4? Where was that? Hold on. On PC0. Oh, all right, let's have a chuckle. PC0. There it is. Uh, 5-volt tolerant. So the first 2 pins are 5-volt tolerant, the second 2 pins are only 3.3-volt tolerant. You know, if you just use PC0, 1, 2, 3, you'd have 4 5-volt tolerant pins. Things like this. Just many things about this design that I wouldn't do that way. So, let me make a note on the schematic about that. While we're here, you know. Five-volt tolerant. Not 5-volt tolerant. Yeah, I suppose. Yeah, these ones and these ones. There we go. Yeah. Good to know. Good to know. All right then. So that's the existing board. Now, the existing board has external stepper motor drivers. But I need to design a board that can be used as a drop-in replacement on this machine. But can also be used by other machines in the future. I'm trying to find this. Here we go. So I want it to be a drop-in replacement for this machine. So I want to take out the control board that's in the machine and plop in a different one. I'm trying to find a photo of an overview of the inside of the machine for a moment. Yeah, this one. Yeah, it's not great. Could do with a better photo. Yeah, that one. There we go. So I want to take that control board out and just drop in a new one where it sits. And then at a later date, maybe I want to take out the stepper motor drivers over here and over here. And other people that don't have this machine, I want this new board that I'm going to create to be usable by them on whatever machine they're creating. So we're designing for this machine and for other machines as well. And we also wanted to run with the MakerPnP architecture. I talked about the architecture of the MakerPnP software in the previous live streams, so you can go back and watch sort of like the last half of that if you want to know more about that. But the idea with the architecture is that there can be multiple control boards in the system. Let me see if I can find that file, just quickly bring that up. this, this sketch. So the idea is you've got a client bit of software, you've got a server bit of software which runs on like a Raspberry Pi or a single board computer, and then you've got one or more control boards, and each of these control boards can talk to other control boards as well, and then all the communication flows between them all. So that's the architecture that I'm designing for. And then we've also got cameras and so on like that. Where do the cameras connect up to and so on, all that kind of stuff. And I also mentioned that there may be more than one control board, and each control board may be physically located in a different place, and some of them might be identical, and some of them might be teeny tiny little control boards with an MCU on it. So for example, you could have the main control board in the base of the machine, and then like we see on my machine here, on the back of the head there is another PCB, and all the signals for this are routed through a long cable on the top of the machine, the drag cable, right? But some signals don't travel well over long distances, so sometimes it's better to deal with the signals wherever they're generated, and then have a data stream over a long cable and power, and that's about it, instead of like loads of digital I/O and PWM signals and a whole bunch of other things. So maybe some of it's better on the head and some of it's better inside the machine, and there's sort of a balance between it. But either way, there may be more than one control board. So imagine, you had a new version of this PCB on the back of the head with an MCU on it, and then have the two control boards talk to the server. Right, that's the idea. So let's talk about what we're going to actually design and get on to designing it. So in the base of the machine, we're taking out this board and we're putting something else in there. So we need a board that has the same physical mounting holes for the main control board. Let me just bring that up. So the mounting, well, I measured the PCB and I measured the mounting holes and their offsets from the edge of it. So I've got that. Here we go. Bring that up. Right. Let's turn off the rat's nests. Oh. So that's basically the control board, and these are all the components that would be on it if I was to replicate the schematic, which is incomplete. So yeah, so all of these things plus all the connectors need to fit in this space. We can have a quick 3D view and have a chuckle. Oh, sorry about that. That's a bit bright, wasn't it? Okay, there's not a dark mode for the PCB. So here we can see a PCB, and here we can see a myriad of components. So that's kind of the scope of like the main controller, where it needs to fit. But if we want stepper motors and other additional peripherals and things, we want some kind of expansion. So after a little bit of thought on this, well, quite a lot of thought, and looking at how some other people do things in the 3D printer space, because there's a lot of people doing control boards which are similar for 3D printers but also not. So Big Tree Tech, I was hoping that would come up with the first thing, but no. Big Tree Tech make control boards. It's not an endorsement of any of their products, I'm just showing you it because it's interesting. They do boards like this, for instance, which have the usual sort of like 2.54 mil pitch, 0.1 inch pitch stepper motor drivers that can plug in, or you can plug in their little stepper motor drivers that look like this. They have various different ones, and I'm like, yeah, it's kind of interesting. I kind of like the way that they make these replaceable modules. It's kind of neat. But at the same time, I've already got stepper motor drivers. I don't need stepper motor drivers for the inside of my machine. But if I want to replace them in the future, maybe I want a better stepper motor driver to make the machine more betterer. It's not yet proven how this system could work with new software, so maybe we need to upgrade the stepper motor drivers, or maybe we don't. Maybe everything's fine. I don't know. But the eventuality is that I might want to change it, and other people that don't have the same machine, that want to use the same board to do development work on the software or just to fit it to their machine, they're going to need some stepper motor drivers, and it might not have any. So wouldn't it be nice if we designed it so we could plug stepper motor drivers into it? So my idea, and you guys can tell me if I'm crazy or not here, is to do something like this. I'm trying to find the files. So many files, too many files. My idea is to do something like this. So we have a board in the same sort of shape as the existing board, and then we have like 3 or 4 expansion sockets on the side of it. Not vertical mount ones. So with pick and place machines, the available space to use for the machines is often underneath the bed. So you have the bed of the machine, and then underneath it you've got a large space. And this space is normally quite wide and quite large. So a thin PCB that's on a single sort of plane is probably better than one that's like flat and then has things sticking up on it. I don't like the idea of like big chunky heavy boards sticking vertically upwards. They're good for heat dissipation and things like that. But they're not good the moment you ever want to plug a connector into one of them, because then you've got a cable hanging off it and you could accidentally yank the cable, and then you've got a socket and you've got a PCB stuck into it and you can yank it over and break things. I just think it's a bad idea. In PCs, like desktop computers and so on, they do this. They have a motherboard and it's got sockets in it and the sockets face upwards, but you've also got mechanical support at the back of it. You've got a bracket for the cards to sit in, right? But then you need a bracket, you need mechanical support and all this kind of thing. So it's like, yeah, vertical, no. So I think horizontal expansion is probably for the best in this. And if you've got a machine which has already got mounting holes in the right place, and you're making like an expansion card which sticks out the side of it, the chances of those holes being in the right place are slim to none. So, but that's okay, because you can plug the expansion card in, you can plug a nylon PCB standoff through the bottom of it, and then it's got adhesive on the bottom of it, which can then be used to stick to the base of an existing machine, like my one. Or if you were to design a machine from scratch, you could drill some holes and then put standoffs in the right place. Kind of like you do for a motherboard. So you have like an ATX like motherboard space inside a chassis, and then it has holes for standoffs to go, and you screw the ones in that you want depending on the size of the motherboard that you've got. So I think it's kind of practical in that regard. That then leads us on to connectors. So yesterday we were looking at connectors, and this is sort of fresh on my mind, so I'm going to talk about this a little bit first. So there's a bunch of different connectors that you can use for this kind of thing. Yeah, it's complicated. It's complicated. Where are we? Let's have a look. So if we hop onto LCSC for a moment and see what we can find, right? Now, these connectors, the ones I'm looking at, I mean, you couldn't. Let's talk about what we could use and why they're not ideal. So if we go rectangular connectors and then sockets, right? You've got the usual 2.54mm sockets, and they do right angle versions of these. And you can either have through hole or surface mount ones. But let's just have a quick look at the surface mount ones. And let's say we want 2 rows of 20 pins. Oh, okay, well maybe not 2. Damn it. Let's have 2 rows of 10 pins. I'm trying to find ones that are in stock. Oh, come on. Wait, what's happened to this? Surface mount right angle? Yeah. I'm trying to find a 2-row one of these. Yeah, there's one. So these things look like that, right? So you can have like these on the motherboard, and they're probably okay. But then on the card that plugs into it, you've got a bunch of pins sticking out. And what happens with pins? They get bent, and the insertion force for pins, like, yeah, you can plug them in. Yeah, they're okay. They're okay. They're quite chunky. They have quite high current carrying capacity on these things as well. It's not too bad. Like 3 amps per pin. It's pretty decent. Physical space. They're quite chunky. So if we think about the maths for the amount of space that we've got for a moment. So if we were to try and do, this, the distance here from the top to the bottom is, hold on a moment, I've forgotten. This one. Yeah, 20 centimeters. And that divides nicely by 4, so then you got 5 centimeters per expansion thing. So that's the kind of distance we're talking about. So only 5 centimeters for one expansion card, and then you have 3 or 4 of them. This kind of thing. So here I drew it with like 2 large ones and then 1 small one. But you can just make them longer, so I don't think they need to be sort of different sized ones. I think if they're all the same size, it'd probably be just fine. So 4, I think, is the number that I'm going to go for. Yeah. So going back to connectors for a moment. This is the other type of connector that we have. These ones are really weird, these connectors are. Let's see if I can zoom this in a little bit. These connectors like this. These connectors are very interesting. What they do, they slide over the edge of the PCB. And this allows you to have another PCB on the same plane. So if we do paint for a moment, right? So, let me fill this in with black, quick. My eyes, there we go. So if you've got one of these connectors, and imagine you've got your PCB. I'm just going to do this freehand. Right, this is one PCB, and then the connector goes like this over the end of it. It goes like that. And then the next PCB comes in from the side and goes into it, goes like that. That's how it works. So imagine that you've got your screw holes in this existing PCB. You know, you've got a standoff, which is, I don't know, let me come down a little bit further. You've got your standoff, and then you've got your chassis. What it means is you can use the same standoffs on the expansion cards, and the height of all these is the same. And then you can put your screw in through the top, which goes through into the standoff, right? Something like that. Hopefully that makes sense. Let's pull that up a bit. There we go. The other interesting thing about this is that you only need to buy one thing. So you only buy one thing, and it only goes on the left-hand board. Another interesting thing about this is PCB thickness. These connectors on the left come in different sizes. So this PCB here, hold on, let me draw that properly. You've got this distance over here, and then you can have a different distance over here. And let's call this M. Oh, no. And then let's call this one K. Right. So when this connector slides over the PCB on the left-hand side, the dimension of this connector is the distance between these sort of semi-spring loaded pins, right? And those pins are either bent in like a certain way. The contacts are bent in these things. So one of the contacts, I guess, probably looks something like this. Yeah, something like this. I don't know. You get the idea. And then, depending on the thickness of the PCB, this contact is in a slightly different position and is bent slightly differently. So you need to make sure you buy the right connectors for the thickness of the PCB that you want. And then, of course, you have to see, well, how do you manufacture and solder this thing on? It's kind of weird, because if you look at this connector, it's got pads. It needs pads on both sides of it, but it's sort of surface mount and it's sort of not. It's kind of weird. So apparently the way that they attach these things is with wave soldering. I wasn't entirely sure how they actually assembled this, because you've got to. Do you have to support the connector and wave solder it on one side? And then they're kind of weird. They're kind of weird. But I think I'm going to use these connectors versus the other things that I looked at. There's like blade connectors, but they don't come in like many pins. Is my audio working properly? I'm not sure what's happening with my audio. OBS is being a bit funky. Hopefully the stream's okay. Yeah. Okay. Yeah. So I think these are the connectors I'm going to use. Yeah. My OBS is being a bit funky. Sorry about that. So I think this is what we're going to do. So let me just save this. Connectors. And these are called straddle connectors. And these are just PCIe connectors. So you get like the X1 version and you get the X4 version and so on. And if we have a look at the data sheet for one of these things, it details the PCB thickness option over here. This is why I called it dimension K. Although I think I had the M and the K the wrong way around on my little diagram. And then it also details the specifications for the PCB that slides in it and the size that needs to be. So it's quite well documented, these things are. And lots of different manufacturers make them with the same layout, which is good. And they're quite cheap. And there are cheaper ones as well. So these aren't too bad in terms of like BOM costs and so on. And remember that you only need one of them as well. So when you're making the expansion cards, you don't need another connector that goes into it. There are some other concerns with using these connectors. One is that the edge of the PCB that slides into the connector needs to be chamfered. And if you imagine that you've got your copper on the side of the PCB for the contact over here, it needs to be that when the chamfering tool comes along and runs along the edge of the board, that it doesn't slice off the copper, and there can't be any burrs remaining of like bits of copper that get chewed up. Otherwise they're going to short each other out and it's going to be really bad for the connector. So that's one thing. And then you also need the same kind of chamfering on the PCB that the connector fits onto. So it does increase the cost of making the PCB because you need to run a chamfering tool on the edge of both the slot-in card and the card that has the connector on it, so that the pins can push against the side of it and then open up and then go over the connectors before it's soldered. So that was interesting. The expansion cards also need a pretty tight tolerance on the actual dimensions of the routed edge of the board and the copper pads that they're close to. But I see a lot of PCI cards out there in the wild, so the manufacturers can probably do it pretty good, because this is the technology that we're using. This is like PCI cards, right? So I think we should be okay. And happily, going back to the dimensions for a moment, so we had our 20mm space, 200mm space, 20cm space. That happily divides by 4 quite nicely, and the largest dimension, the width of a 64-pin version of this, is 48.8. So that means we can quite happily put 4 of these next to each other on the board. So I'm just thinking about what to do next. We could do that next. Should we actually get some stuff done and then come back and talk about some other things? I'm hesitating because the chance of there being a footprint for one of these things is like... Okay, let's see if there's a footprint for one of these things. Let's go to that... I mean, there will be in the easy EDA ones, right? Because... let's have a look. But they don't have a way to export this. Not unless you download their software, install it, and then export it and so on this. But let's have a look on SnapMagic. Is it this? No, Snap EDA. Is it this? This one. Yeah, here we go. PCI. Let's just have a quick search. Yeah, okay. Really? Kind of. I want like a. I mean, we've got PCI ones like this. Yeah, I don't think this is the best way of trying to find one of these footprints for this. We need a part number, but the problem is the part numbers are all from like random Chinese manufacturers. Let's go on to LCSC for a moment and find the. I suppose we could have a quick search for this. The chance of this thing being in here. No. No. That's what I thought. PCI EX4, clamping plate, right angle, apply. I'm just looking for another one with the same. Right, that's the one we were looking at. But there's other ones from other manufacturers. This one is another one. The XKB ones. There might be one of these. It'd be nice if there was just a. I kind of need a 3D model as well. The XKB ones have good 3D models as well. So. Let's search for the part. No. No. Let's just. Oh. No, they just. Oh, they just tag it. Okay, fine. We're going to have to make a footprint to do it. So I'm going to leave this for later. Right, we'll get rid of that. So that's the idea of the concept of the connectors for expansion. So let's talk about requirements a little bit more before we dive into actually making stuff. Requirements. Yeah. Let me find my requirements. Here we go. Requirements. Yeah. So I was thinking about this. It's been off and on in my brain for about a year or so. This has. But yesterday I made this list of what I know I need based on the existing control board and what I've decided that would be good for the MakerPnP software, having started writing some of that and fleshing that out a little bit. So we need a fast MCU. Let's talk about MCUs for a minute. The original one was using an F407. It's fine. There's going to be F407s around until the end of time, probably, because they're so widely used. A modern sort of better version of an F407 is the H743. But the H743 is getting a little bit long in the tooth these days. And perhaps there's better alternatives. So Where's the 8743? So the 8743 is this one. It's available in some different size packages, and there's another data sheet for the larger packages as well. One interesting thing about the 8743, which I think I've just sorry, I clicked something accidentally. Where is it? Yep, here we go. This table details the differences between the different processors. So we've got amounts of RAM and flash and things like this. It's good. Nothing more to be said. There's plenty. And then we come to timers. So we've got high resolution timers. This is the HRTIM peripheral. We've got general purpose timers, advanced PWM control timers, basic powers, and so on. It doesn't really tell you on this little table like the details, the differences between the timers. Again, here it's got the timers here, but like, are they all the same? No, they are not the same. Are they all like 32-bit or 64-bit, or how many bits are there for each one? What's the resolution of each of those timers? How are they connected? Do they share the same clock? You know, things like that. Let's see if we can find the detail of the timers. It was down here somewhere. Come on, there we are. And this is where the detail of the timer is. So what we're looking for, if we've got 4 expansion slots, is to have sufficient pins so that each expansion slot can support 2 stepper motors, 2 stepper motor drivers. If you're doing stepper motor drivers and you want encoders as well, then that means you need 4 timer channels, because you've got the leading edge and the trailing edge of each encoder. So that's 2 pins, and then you're trying to do 2 stepper motors, so you need 4 pins, and therefore you need 1 timer with 4 pins on it to do 2 encoders. So it would be nice if there were 4 identical timers that we could use, 1 for each expansion slot. So can we find 4 identical timers, each of which has 4 channels? That's the question. So we've got TIM2 and TIM5. One's 32-bit and the other one's 16-bit. And then we're looking for the amount of channels that they've got. So we've got 4, which is the number that we need, and then 4. And the answer is no. There are not 4 identical timers in an H743. That sucks. But that's okay, because we have an H725. So let's check this and see. Yeah. So let's see if we can find the same table in this. Description, functional description. Have we got timers somewhere? Okay. Timers. Here we go. Let's have a look. Oh, no. Oh, there they are. Happy days. So we've got 4 identical timers, TIM2, 5, 23 and 24, all 32-bit, all have 4 channels. That's what we need for this system. So we could use an 8743, but we're not going to, for this primary reason. This is really weird that this ends up being one of the primary reasons not to use an 8743, because an 8743 is very widely used. Yeah. So we've got an H725. Yeah. Let's have a quick look at the details of these timers before we get too carried away here. So STM32 H725 thus. So what we want is the reference manual, this. I do like it how ST make their documentation quite easy to find. Data sheets, no reference. MCU. Mosh. Alright, we've saved that. So, timers. The devil is in the details. Right, general purpose timers. So, it was 2, 5, 23 and 24. 2, 5, 23 and 24. Let's look at the block diagram. Encoder interface. Interesting. So the signals that go into the encoder interface are the TIFP1 signals, and TIFP1 comes from here, and 1 comes from here, and then 1 comes from here, and 1 comes from here. So it looks like you get 1 encoder per timer. That's not really what we wanted. Nuts. Ideally what we wanted is 2 encoders, or an encoder interface that supported 2 motors. 1 timer that supported 2 encoders. Hi Negvorsa, who's just joined the chat. Yeah, so that's annoying. I had a feeling that this might be the case. So, yeah. Okay. All is not lost. There are more timers. There are more timers. Let's have a look at Tim1 for a moment. Okay, so where are we? Let's just have a quick look at the encoders. So each encoder only ever uses 2 channels, right? Let's have a look at some other ones. So there's no encoder on this one. No encoder on this one either. Basic time is 6 and 7. You don't really use 6 and 7 for this purpose. So, yeah. Yeah. Okay. Well, so maybe the first 2 slots are special, and then the other 2 slots are less special, and we put the timers on. Wouldn't it be nice if we had the I/O that we wanted? Well, there's a way that you can make the I/O that you want, and that's with an FPGA. So with an FPGA, you've got a bunch of transistors essentially, or gates, and you can program all these gates and connect them to each other in a way that allows you to construct peripherals. So, given that there aren't enough encoder interfaces on an H725, spread across the amount of timers that we want, let's make each of the expansion slots identical, right, using those 4 timers, but then also fit an FPGA to the board that allows and then routes some of those signals from the FPGA to those expansion connectors. And then in the future, when we're designing various different boards, we can create a board and then create some software to run on the FPGA that turns some of the FPGA IOs into encoder interfaces. Problem solved. So, the idea, and if you are paying attention closely to this requirements document, you might have noticed that it said FPGA there. And for exact reasons like this, that we literally just discovered, this is the kind of reason why I want an FPGA in this solution that I'm going to make. Because we don't really know exactly what we're going to need in the future. And there's lots of things we could do in the future. And an FPGA is a sort of way to de-risk having a control board and a system from unknown future requirements. And also for unknown technical issues. So, I don't know, maybe you want a system where two motors are coordinated extremely precisely. For this machine, I can't think of that many reasons why they would need to be, why I would need that. Because I've got X, I've got Y, I've got Z, which does two things, and then I've got the feeders. And there's nothing on this particular machine that needs like precise coordination between two motors. But if there was such a case, and you found out that you couldn't do this precise timing, like jitter-free kind of stepped at the exact moment in time on both outputs, for instance, for a stepper motor, then you could do it with an FPGA. But if you can do it with an MCU, and you can do it with the FPGA, and you've got a peripheral board which has got a step output pin and a direction output pin, they've got to be wired to something, the expansion board socket, right? But then on the other side of the expansion board socket, you've got your MCU and you've got your FPGA, and maybe this can't do it, but this one can. So somehow you need to say, well, I want this output to be using the MCU today, and then in the future I might want to change this output to be using the FPGA. Now, the simple answer for this is jumpers. And I'm going to go with the simple answer so that I don't have to do any FPGA software to make the system work initially. Because FPGA, I don't know much about FPGAs. It's going to be a giant time sink. What we could do is take the MCU signal, route it to the FPGA, write some software on the FPGA that then outputted that signal onto the expansion connector. And then have the FPGA decide whether it was going to use one of its internal software-based hardware peripherals, software-designed hardware peripheral, I suppose, for that output, or whether the MCU should be used for that output, and then it could switch between one or the other for a given pin. You could do that. We could actually technically do both, I suppose, couldn't we? Let me think about that. Hold on. Noise. Signal integrity. These ideas are bouncing around in my head now. Let me just fill this with black. I wish there was a way of making it so you could start paint in dark mode. Still, there we are. So I suppose if you've got... Oh dear, don't do that. If you've got Mr. MCU over here on the left-hand side, Here's Mr. S. Here's that, and then here's the FPGA, and then here's an expansion connector. Let me make that a bit different. And then I've got a signal, and it comes out it goes to the expansion. Right? Great. And we've got a signal coming out of here, and it goes to this. Now, if we wanted that flexibility, and we want to use the same pin, right, we can have a jumper that goes over here, which then allows this pin to either go to here or to go to here, right? So then we can change this pin to be FPGA or the other one. But I suppose technically what we could do is route this over to the FPGA as well, right? And then leave this here as it is, which isn't going to be great for like signal integrity, but if you do the routing so that this little jumper thing is as close to this as possible, and all these traces are short except the one that goes from the output of the jumper to the thingy, it's probably going to be fine. We're not talking about super high frequency signals here anyway, so it should be fine. So what I mean by that is we've got this, and we move it up here. You know, we want that jumper to be as close to these two devices as possible. So then, the idea then is that with your MCU, oh, wrong button. With your MCU and your FPGA, the idea is that then we can route one signal to the expansion connector using a jumper, or we can put it on the FPGA side and then have the FPGA either create the signal, because this is a different pin over here, or we can route the signal through the FPGA. Let me do that in a different colour. It was a bit too phallic. There we go. That's the idea. So, flexible I/O structure. That's what we're going to do. This allows us to do many things now without even touching the FPGA, and also many more things in the future if we need to. So that's the idea, that's the concept here. Let me save this as pin routing, signal routing and selection. All right. So let's go back to the requirements list. So this is one of the things. This is one of the reasons why I want an FPGA on there, is to allow for the unknown, and also so that I can fiddle around with FPGAs, because I'm sure it'll be fun. Because apparently you can write code for FPGAs in Rust, or a language that's very similar to Rust, with the same Rust syntax, and have it compile down and so on, instead of using these older tools with bad error messages and things like this. You can use something else. But we'll get to that at some point. All right, let's go through this list. My thoughts and rationale behind what's going on here. So, an Ethernet port. I want an Ethernet port. Currently, I'm using on my bench over here. I'm doing, I've got an 8743 and an 8723 over here, and they've both got Ethernets, and they're both connecting to the software that I've created, and that's fine. And Ethernet seems like a good way of getting machines out, kind of talking to your machine. If you've got the GUI on your desktop computer, and you've got like the Raspberry Pi in your machine, but it doesn't have a display on it. Right. My machine's going to have two displays on it, the touchscreen one and also another monitor above it, so I can display the cameras and display the Gerbers and display the list of components on a bigger screen, but having a nice way of interacting with the machine when you need to babysit it and set it up and start jobs and things. So we need flexibility in the communication depending on where the screen is going to be, essentially. We could use USB for it as well, and indeed we do want to have a USB socket. So I mentioned down here on the external facing ports, front panel USB socket, so you can plug like a USB stick into it, Ethernet port and the USB port. Currently the machine behind me only has that front facing USB socket, so we need to make a hole in it and then make up a little board to stick on the side with two ports on it. So Ethernet port, the problem then comes, it's like you plug a cable into it, it's like, well, do you know if the port's working or not? Normally you know if a port is working because it has lights on the port that you plug it into on a good hub, right? And the same on the back of your computer. You plug it in, it's got a couple of lights on it. But then you need the Ethernet signals going to it, and you need like some power to light some LEDs. So then you need the Ethernet signals and power and I/O signals from the MCU. Yeah, which is a bit annoying. We don't have to have that, but it would be nice to have that. So therefore we need an Ethernet LED port as well. So if you imagine you've got your control board, and then you've got a tiny little board stuck at the back of the machine, which has an RJ45 in, RJ45 out, two sockets, and then it has a header pins or something like that on the inside, and then it has LEDs that face outwards. And then your main control board will have Ethernet port on it, and then you plug that into the port on the back of the machine, and then on the outside of the machine you plug in your cable to your hub. That's the idea there. Going back to the expansion connectors for a moment, let me do a new little sketch here. Sorry about the eyes. Right, so if we've got our PCB and we've got our connector that sits over the edge of the board, does, right? And then we've got our MCU and we've got our FPGA, and then we've got a bunch of jumpers, right? That's the shape of it at the moment. Just talking about the expansion things. Right, and then you've got an expansion card which plugs in, I don't know, maybe one's long like this, and maybe this one's the same, and maybe this one's like a short one or something, you know. Who knows what you want? And then you've got another one up here. Right. That's the kind of idea. So what we want on this, we've decided that we want timers, so per port list. So Paint's probably not the best program to do this in. Probably should use a vector-based drawing program. Let's copy this out of here. Let's fire up Krita. I am going to struggle with this, but you know, please bear with me. Create from clipboard. Do it. Just do it. Too many questions. Okay. So, there we go. Text. Yeah. Can we do text? Yeah, okay. Text. Save. Okay. Alright, so. Yeah. Because in this we can move things around and then come back and edit it, right? So, we want a timer with encoder. Well, let's say 2x timer channels with encoder inputs. Right, and this is per port. Other things that we need are step and direction. So we've got 2x step plus direction, right? Yeah, because that's how step motors work. And probably we need like maybe one independent enable signals. Maybe you want to enable each one independently, which would probably be nice for testing things. Let's just say 2x enable signals. Given the FPGA MCU combination here, I don't think we're going to be running out of I/O signals anytime soon. But what I really kind of want is a system that works without there being any FPGA software whatsoever. So maybe we have to change this to 1. I don't know. We'll see. We want SPI connectivity. We want I2C connectivity. For SPI connectivity, we need the clock signal, we need the MISO, and the MOSI. And if we're controlling 2 motors, then we need to select one or the other stepper motor driver, right? So we need 2 NSS, well, 2 CS signals. I'm going to say 1 is NSS. What do I mean by CS versus NSS? On STM32 processors, you have the SPI peripheral. Let's find it. You have the SPI peripheral, right? Let's find the block diagram. Here we go. Other manufacturers of MCUs do a better job. This is what the ST ones look like, mostly. The important point here is that there's only one SS output. SS is the slave select, so you toggle this when you're talking to a particular chip. If you've got 2 particular chips, you can route the SPI signals to both chips, but each chip needs its own slave select signal. But in the the ST peripherals, there is only one hardware-driven slave select signal. So, it's just not quite as nice. Like the ESP32 ones, for instance, they have SPI peripherals which support multiple hardware-driven slave select signals, but ST don't. So, going back to the list, we want 2 slave select signals, CS, SS, cable select, slave select. So we want 2 slave select signals, but only one of them could be hardware. So therefore, we need, and because this is per port, we need many SPI ports on this. Can we resize this line? No, it doesn't do it. Oh no, what did I do? Oh. I'm failing to use Krita now. Oh, there it is. Font size. No, let's put it on 7. That's fine. There we go. Okay. So, this is our list so far. So let's go back to the reference manual and see how many SPI peripherals we potentially have. Yeah. Where's the list? Show me the list. Here we are. Timers, COM interfaces. Here we go. SPI peripherals. It varies depending on how many pins you're using. So, hold on. Trying to find the list. Kind of want to know about the IOs, which one's which. But the smallest one has 4, which is good. Because I don't think currently we need any onboard SPI devices. Yeah. So we've got 4 SPI peripherals that we can use. This is good. If we go to the larger ones, and I was initially thinking about like an LQFP144. Ideally, if we can get away with a 100-pin one, good. But I'm not sure whether we can. So we might be using the LQFP44. Let's fire up CubeMX for a moment. Let's get rid of this. Let's create a new project. Okay. So we're going to search for STM32H725. There's a bunch of different ones. Here they all are. So let's have a look at the data sheet for a moment. Manufacturing. Let's talk about manufacturing for a moment. I want that machine to be able to be used to make this control board. My reflow oven is not very big. Yeah. Now, going back to those connectors that I talked about earlier. Yes, I want my machine to do it. But I don't have a wave soldering machine, and I don't really want to be soldering those connectors on by hand that we talked about. But for like initial small limited runs, that machine can be used to do it. It'd be fine. And then if I did a larger run of these boards, then I'd have some company somewhere and make them. So, connectors aside, I want this machine to place all the parts. So, and I need to be able to assemble it and test it here, right? So, manufacturing tolerances, BGAs, and things like this. LQFP144, not so bad. So, the LQFP144s are like this kind of thing, right? Fine. The pitch between the pins is 0.5 millimeters. And then if you don't get your solder paste right, you end up bridging things. So you've got to make sure you get your solder paste right. Yeah. I've had success in doing designs which use BGA chips. For example, on this, there is a BGA chip in the middle there, and there's also an ESP32 on there which has 0.4 millimeter pitch pads. So I know I can do the ST BGAs which are these TFBGA 100s. These ones. And if we look at the package information for these, the TFBGA 100s, here they are, have a 0.8mm pitch, which is wider, as there's more space between each pin on a TFBGA than there is on an LQFP, which I thought was quite interesting. So there's actually better manufacturing tolerances on this particular BGA than there is with an LQFP 144. Curious, no? Yeah, so I've used these TFBGA 100s. Now, I am a little bit hesitant to use anything that's got a pitch that's much smaller than that when it comes to BGAs. So let's have a quick look at this UFBGA 176 plus 25. This is what I'm thinking about trying. I'm not sure yet. I'm not sure. Because these have a 0.65mm pitch, but the pads for it are, where are they? The diameter of the pad is 0.3mm, right? The other BGAs, for instance, the UFBGA 169s have a smaller pad and the pitch is smaller as well. So the pitch on the UFBJs is the same as the pitch on an LQFP, but you need to be a lot more precise when you're placing it, because you can't rework BGAs in the same way that you can rework LQFPs. So if you've got an LQFP and it's slightly down wrong, and then you've got two pads that are joined on it next to each other, you can rework it and fix those two pads. With a BGA, if you put it down wrong, you don't know that you've accidentally bridged two pads on it. So your placement and your solder paste for these things has got to be bang on. So I'm a little bit hesitant about using a UFBGA 176. Is there a way to fix this? Does a UFBGA 176 fit in the same dimensions that an LQFP does? So can we design for a UFBGA 176 and fit an LQFP over the top of it if it doesn't work out, and use fewer pins? This is what I'm thinking. Let's see. What are the physical dimensions of the outside of this? So the physical dimensions is E and D. So we've got E 10 by 9. No, 10 by 10, sorry. So it's 10 by 10. Now, let's have a look at the footprint of an LQFP 144. And I suppose we could just use the LQFP 176 if it doesn't fit on the LQFP 144. So 10 by 10 is what we're after. So this is the dimensions here. So what we're looking for is the footprint. Here it is. And we can see that we've got a ginormous 17.85 millimeters to slap a BGA in the middle of if we really wanted to. So yes, that idea would work if we needed to do that. So we could design a PCB which has the two footprints. We've got the BGA footprint. Let's go back to this for a moment. No, Krita. Where's Krita gone? This. So if we imagine we've got this, and I don't know, let's draw an orange box around it. Oh. and we'd have an LQFP around a BGA. Something like that. And this allows me to design for a 176 BGA and maybe fit an LQFP instead as well. I don't know. I'm still running around with this idea. I don't know. But yeah, potentially using the BGA with the larger manufacturing tolerances. So let's go back to part numbers. So if we assume that we're using the 144 as the bare minimum, well, shall we start with 100 and then decisions. decisions. Right. Package. LKFP 140. Oh, wow, that's 24 millimeters. That's huge. Yeah. Okay. Let's just pick. Let's just pick the LQFP 144 and go from there. Let's forget the BGAs for now. The reason I'm thinking this is because if we start with a limited set of pins, the likelihood of those pins also being available on a larger package is higher. So if we design for the 144 and then run out of pins, we can switch up to the 176. So let's do that. And it doesn't really matter which one of these I pick. This is just the temperature range. So yeah, let's go for it. Yes, decisions. So many decisions. All right. So let's turn on the timers that we want. It was 2, 5, 23 and 24, wasn't it? 2. I want the encoder. Input, I suppose. So we're going to turn those two on. TIM2, and we can remap the pins in a bit, but let's just get the basics there first. And we'll turn on the other channels as well on the same time, because why wouldn't you? And then 23 and 24. So right. Oh, I wish ST processors had like a more flexible I/O matrix or something, but they do not. Well, that's annoying, isn't it? One pin's all the way out here. Thanks, ST. Thanks. What happened? Oh, I haven't turned 24 on yet. There we go. That would help. I might have only got 3 timers. Oh dear. Really? Oh. Wait, what? Huh. let's just put this on PnP. All right, yeah, look. That's interesting. So TIM24, one of the timers that we need, doesn't have pins. Yeah. Okay. Let's have a look at that in the datasheet. Nuts. Datasheet. Here we go. Pin outs. TIM24CH1. Right. So we're looking at the fourth column, right? And then CH2. Yeah. So TIM24CH2 is not available unless you go up to the LQFP 176 or the UFBGA 176. Well, that's annoying, isn't it? Well, okay then. Not that it really matters for this, but I'm kind of curious to how much these cost. LQFP 176. Oh, what happened there? Where's it gone? Let's just click a random one. I just want to find the category. Here we go. LQFP 176. Oh, they don't even have the other UFBGA one. That's kind of weird. Okay, fine. It's fine. 13 bucks. This isn't designed down to a price, this board. It's like, it costs what it costs. It's going to be cool, and it costs what it costs. We're going to use the 176. I suppose we should check the lead times on these. So the package is the IGT package. Kind of curious about the lead times on these now, though. Yeah, they've got some. IGK6. Which one's the K6? Oh look, that's the UFBGA. Is it? Which one's which? I'm trying to cross-reference which part is actually which. I suppose we could use the CubeMX to do it. Hold on. ST don't make it easy in the data sheets. You've got the data sheets, you've got the reference manuals. It's like, oh, come on. But they do make it easy in the MCU selector. This thing. Yeah, let's see. And we're back to the UFBGA 17625. Joy of joys. Okay. Fine. Fine. Okay, so let's change the MCU. I forget how to do it. this was it. Here it is. Pin out compatible MCUs. Fine. Save the file. UMX. Just do it. Stop. No, not LQFB. UFBGA. Well, I suppose let's pick that. Search. So just with the timers, we've got that. This is good. Okay, fine. So IG, we said. It's fine. All right. It's annoying. Just want 4 encoder interfaces and 4 identical timers. We've got to switch up to a 176 pin chip to do this, ST. Are you watching this? Can you sort it out and put a GPIO mux in your processors, please? Four identical timers with encoders. That's all I want. That's all I want. Here we go. Okay, actually, technically I wanted a little bit more. I wanted the other 2 timers channels to be available on the expansion connectors. But, yeah. Input capture. Indirect mode. No. Direct mode. Here we go. So now we've actually got the right thing. There we go. Yeah. Thanks. Thanks, ST. Thanks. Oh my god. This is huge. So let's have a quick look at the alternate pins for this and see if we can bring some sanity to this. No. 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 Like, why is this all the way out there? What else is on this pin as well? I'm kind of curious. Let's have a look. I know we're going to be needing these things, and there's not that. And then what's on? Where was it? Oh, joking. So what I'm looking at is the alternate pin mapping. So in the datasheet for these STM processors, you've got a pin, and it can only be used for particular functions, right? And those particular functions are fixed and cannot be changed. So if you want to have SPI 6 clock on any random pin on the MCU, you can't do that. You can only use specific pins that it's available on. So you've got this juggling act between the alternate function mapping and the available pins and the peripherals that you want to use. And I've ended up with pins that are all over the place. What I want is 4 adjacent pins that I can route to each of the 4 expansion sockets. What I don't want is a random pin on the other side of the processor for one of the slots, which I also need for like the SPI. So let's turn on the SPIs. Okay. Now, clocks. Let's look at clocks for a moment. Yeah. Clocks. Datasheet. Here we go. Clocks. I suppose actually we could use the STM QMX for this. So if we go clock configuration, yeah, here we go. Each peripheral is controlled by a clock. Ideally, if I've got 4 identical expansion connectors, then I probably want all of the SPI peripherals to be clocked. using the same clock source. So SPI 1, 2, and 3 share the same clock source, and then we've got, what else have we got? Where are the other SPIs? SPI 6 is very flexible, and SPI 4 and 5 share the same clock. So probably what we want is SPI 2, 3, 4, and 5. Yeah, and then there's DMA. You got to think about the DMA. Where's the DMA? Okay, let's have a look at the data sheet. Not that. DMA, where's the DMA coming from? It's going to take me a moment to find this. There's like a little diagram that I'm searching for. Not that, no. I know, the devil is in the details for this, isn't it? Where is it? It's in the DMA controller in the reference manual. That's where it is. You can't choose your pins unless you've looked at your reference manual. You think you'd be able to choose the pins by looking at the data sheet, but no. Okay. Right. So DMA controller. Here we are. Right. DMA controllers. Use the DMA controller to move data around the system without the CPU having to go copy this byte, copy that byte, copy this byte. You say, DMA controller, take this stuff and put it here. Or timer, tell the DMA controller to do something every time the timer elapses. And when the timer elapses, here's what I want you to do, and then put it here. And you can maybe do a couple of other operations if you chain the operations together. Anyway, you need to know what DMA channels are in use and what DMA controllers are used. If you don't want to overload the system, you want to split the resources between the different DMA controllers. Or maybe you want one DMA controller to be doing one particular thing uninterrupted, and then the other DMA controller does the other things. So you either want to split it, or split the resources if they're used continually across two DMA controllers, or have one type of resource on one DMA controller and another type of resource on the other DMA controller. Since these things are all doing the same thing, it probably makes more sense to have them all on the same controller. Like, identical. So, anyway, the DMA controllers basically have, well, there's a table in here, and you say this DMA controller is connected to this peripheral, like SPI1 or whatever. But there's only a set amount of ways that you can do it, and some peripherals can't be accessed by one DMA controller and some can, so on. Somewhere there's a table, which I'm failing to find. Yes. Yes, it's different. You've got DMA mux now. The older STM peripherals didn't have the DMA mux, so I think our life is a little bit simpler with this. Yeah. And this is a good thing that they added this. You don't get this on the F4. So you say this input goes to this DMA controller, I think now. Inputs to resources. So we've got the various different SPI signals, inputs, which is good. So DMA Mux 1 has SPI 3. Spot the other SPIs. SPI 1, 2, 4, 5. So it has 1, 2, 3, 4, and 5, and this is why I didn't pick 6. And SPI 1, I believe, is slightly more special in some other ways, which I'm failing to remember. And DMA Mux 2 has SPI 6, but it does not have the other SPIs. So, DMA Mux 1, fine. So we can't use SPI 6 for the peripherals. Now, is there anything special about SPI 1? Apart from the fact that lots of the SPI 6 pins are also the same as the SPI 1 pins, which allows you to use the same pins but clock it differently. Serial peripheral head, where is it? Where's my SPI? There. Was there something different about it? Features. Yeah, 4 and 5 are different from 2 and 3, which isn't ideal. And it doesn't have I2S. Huh. But then neither does this one, so that doesn't matter. See, there aren't 4 the same. Like, just make it the same. Just. Why? I want 4, not 3, not 5. A nice even number of things that are the same. Fine. Fine. Yeah. Okay. It is what it is. Good to know that slots, that 2 peripheral slots on my design on this design, 2 peripheral slots are going to be different because of the SPI. But that's the only difference so far. Other than that, I think they're all fairly similar. Okay, fine. So we're going to go with 2, 3, 4, and 5. So back to CubeMX, back to the pin configuration. SPI 2 full duplex master with the hardware slave output signal. Great. And then we do the same for the other ones. Master, and then we see how everything changes. I'm getting hungry. Output signal. Let's have a look. I might need some food. Output signal. Well, that's good. I was able to do that. This is good. Okay, let's turn on Ethernet. Oh dear. Okay, let's not turn on Ethernet. RMI versus MII. I think we only need RMII for this. We don't need the other one. Let me go look at some code. Hold on. It's kind of important because one needs a lot more pins than the other. I can't remember which is which. So firmware, source, firmware. This is for the 8743 that I've been fiddling around with for like experimentations and testing. Somewhere in here we configure some peripherals, then we set up some pins. Here we are. Yes. This is what we did. fairly certain that's RMII, this one. So this conflicts with stuff. Why? What does it conflict with? It conflicts with SPI2 and TIM5. TIM5 channel 2, which is one of the encoder inputs that we need. Oh, no. Please, ST, just GPIO mux, please. Please. I just want my signals. You know, the chip does all the things I need inside, but if it does what it does inside and I can't get them exposed on pins, what good is it? It would just be so much better if there was GPIO mux on STMCEs. Like, it's the number one biggest thing that they're all missing is the GPIO mux. There. All of them. Okay, so this is a problem. And it says and or. So what I'm thinking is that since there are differences between the ports that the expansion ports that we're adding, in that the SPI is slightly different, then perhaps ports 1 and 2 are more special. Or perhaps ports 3 and 4 are more special in a different way, so that you don't put all the special things together. I don't know, should you put all the special things together? Yeah, we've got an FPGA, so... I don't know. So what I'm thinking about doing is putting TIM1 and TIM8 on 2 of the ports. Which means we can probably go back down to the... I don't want to do it. Which probably means we can go back down to the LQFP144. Okay. Right. This is the problem. Let's save this and away we go. Yes, that's fine. Life is not easy. Okay, so let's do a new project. Okay. And we're going to go back to the STM32 H725. No, it doesn't go there. Like, it goes there. Fine. And we're trying to find the LQFP 144. The one with more RAM, yes, that one. That one. Okay. Yes. Right, and we're going to save this as 177 pin. Fine. Okay, so we're going to go back to the timers. And we're going to turn on... well, let's do TIM1 and... because I just really don't like this. My soul is dying inside. Like, yeah, using TIM1 and TIM8 for like 2 encoder inputs is just madness. But we're going to turn that on, and we're going to turn this on. Now, let's have a look at TIM 23 and 24 again. And the problem was that we didn't have channels 3 and 4 on it, on one of these timers, wasn't it? So we got input capture and we got input. Yeah, this one. Just one pin. And it just throws everything into disarray. Disarray. Okay, fine. But I suppose, let's think about this a different way. Let's turn on the Ethernet. Let's turn on the Ethernet before we get too carried away. That one. Let's turn on the SPIs. No output signal. Output signal. Let's go for. If we can do this with the LQFP144, then we're good. And SPF 5. Come on. That's it. Okay, so we've got Ethernet. We've got 2 timers. Now, encoders are one thing, and other timers do other stuff. So we've got some other ones to play with. Let's go back to the datasheet for a moment. Where are we? Datasheet. So 2, 3, 4, 5, 23 and 24 all have the encoder interface. Right. But they weren't all identical. And if we go back to the datasheet, where's the list of timers? Not that. PMA controllers, timers. Come on. Where's that table gone? Who remembers what page it was on? Just never remember this, where these things are. I know what it looks like, but not where it is. Here. This is it. So 3 and 4 were 16-bit. And the other ones were 32-bit. So, hold on a second. Let's have a look at TIM 13 and 14. I don't think they had the... they didn't have the encoder interface, did they? No. So what my thought was to expose TIM 1 and TIM 8 on 2 ports, and then try and find some other timers which were identical, which are sort of smaller, less complete timers that both had either 16 or 32-bit, and all 4 were the same. But even that is not possible. Because these ones have encoders. TIM 3, yeah, right, okay. And then these ones don't. These ones do. It'd be nice if this table listed encoder support, ST, if you're listening, which you're probably not. But it would be nice, because if you're looking at the functional differences between the timers, it would be nice to have it summarised in one place, instead of having to keep cross-referencing everything. Still, there we are. So, TIM24 is a bust. We can't use TIM24 for encoders. We have to use TIM 1 and TIM 8 for encoders. And then that gives us 2 other timers. It's just, there's no good way of doing this. This is crazy. This is hilariously crazy. I just want 4 encoders on 4 timers that are the same. Wait a second. It's worse than that. Because the idea is to have 2 encoders per port. Oh dear. Okay. I think my dream of having 4 identical ports at this point is going out the window. Because it's just not possible. How do we reallocate the resources to the ports? I'm thinking put TIM1 and TIM8 on individual ports, ports 1 and 2. In case you want to use TIM1 and TIM8 to do like field orientated control stuff. Right. Which needs the fancy timers, TIM1 and TIM8. Then take TIM2, 5, 3 and 4 and put 2 and 5 on one. Wait, no. 2 and 3 on one port and 5 and 4 on another port. So that the ports are identical. Yeah, let's do that. Oh my god. What a faff. Notepad. So the thought is port 1, TIM1, port 2. Let's do this. We'll make a list. TIM8. Port 3, who knows? Port 4, don't know. It probably has SPI 5, SPI 4. Let's just make this markdown while we're at it. Ports. So it's going to have TIM1. I suppose I could do a markdown table at this point. Shall I just use Excel for it? Let's just use Excel for it. Text. Pff. Okay, a table will be good here. Port. Peripheral. 1, 2, 3, and 4. Okay, let's say TIM1, TIM8. Timers. Timer 1, timer 2. SPI, SPI 2. I suppose we can do this, can't we? Like that, there we go. And then the second timer is going to be TIM2 and TIM5. No. No, 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 no. Those ones go here. TIM3 and TIM4. So they've got a 16-bit timer, but it's got encoder peripheral input. Okay. Which means we need 2 more times on here, which don't have encoders. Probably TIM23 and TIM24. Because then wait a second. Let me switch this round. Now, Tim 1, 8, 23 and 24 are... Yeah. This means that... Oh, that's supposed to be Tim. Hold on. What have I got going on here? I've got there twice. That's not right. What have I done? Oh, Tim 2 and Tim 5. That's it. So encoder and 16-bit, encoder and 16-bit. Okay. Tim 24 can't have an encoder because one of the pins isn't available, but it's 32-bit. Let's put no encoder 32-bit. Well, this one can have an encoder. Tim... No, I've done it wrong again. This is supposed to be Tim 3, right. So Tim 3 has an encoder, but it's 16-bit. We're trying to get the mapping of all this stuff right. And Tim 4 has an encoder and it's 16-bit. Tim 2 and Tim 5 have an encoder and are 32-bit. Encoder and 32-bit. So what we want let's move those to here, and these to here, and these to here, and these to here. Right, now we get a better picture of what we need, where we need it. Let's save this somewhere. God, I hate the stupid file selector dialog in Excel. It's just so annoying. I don't know what Microsoft are playing at with this stuff. They're not there. This one. Design. Port peripheral mapping. There we go. All right. That's what we have to end up with. All because one pin isn't available on Tim24. At the same time as Ethernet and SPI, because there's no GPIO bugs. Okay, moving on. So let's enable all this stuff in CubeMX. Make sure we've got all this. So let's just enable time, and then we're going to see where this comes unstuck. And this one 4-channel, and we want 2 channels at a minimum. This is going to be chaos because of Tim24. Fine. Tim 1, Tim 8. 4. Tim 3 and Tim 4. So far so good. So we've got all our timer channels for these. Now let's deal with this. Tim 2 and 5. So 2. Let's just do Tim24 first because it's painful. So we've got input capture. We don't have input capture. We don't have an output pin on pin 2, channel 2, or on channel 3, but we do have one on channel 4. Like, why didn't they have it so that 1 and 2 were available or 1 and 3 available and 2 and 4 not available. So at least you can have the same software running on the same timers channels. So because TIM24 is special, we can only use outputs 1 and 4. So to make life easier in terms of software, it would probably be better if we use the same 2 channels on the other timers as well. So let's just say PWM generation on these 2 channels, and we'll see how far we get. So TIM23. No. Wait. Clashes with SPI 5 full duplex. SPI 5 GPIO mux. It would be nice if it told me what pin precisely it clashed with. TIM23 channel 1, which has no alternate pin inputs. Oh, fantastic. Well, that dream has been shattered as well. Thanks, ST. Just... What to do? So this one's got these 3 available. Let's have a look. Where's my list again? Because I see another red flag here. Look. Okay. So 2 of them have got 1 and 4 available. Okay, so TIM2 has got all the pins enabled, so that one's fine. So we can move it anywhere. Right. TIM24 has got 1 and 4. TIM5 can also have 1 and 4. So we've got TIM24 and TIM25 with the same software. Five and 24, I said, right? So 5 goes together, and that goes together like this, and then it's the same software. So this is four channel, 1 and 4 and 1 and 4, right? TIM2, let's turn all these on. TIM2. TIM23. Nope. Wait a second. Hold on a second. I did. Oh, it's got a remap. There's a remap. Hold on. But this doesn't have a remap. Okay, we might be okay. What's a remap? Well, so you know earlier I was talking about the alternate function pin mappings, where I said each pin has a set of functions that it can do. That is true. And then you add on top a sort of semi-GPIO mux, and it's called remap. So there's a bit of a GPIO mux in there somewhere, but not a full one. Just make all pins remappable. Make it not suck. So we wanted 23, ideally to have 4 channels, but this one conflicts with something else, SPI 5 again. So you have to do a remap on that channel. So we need a remap. Where did that end up? No, hold on. No, you still don't get a GPIO pin. No, we're doomed. It doesn't expose it. So let's turn off SPI 5 for a moment. Perhaps we're going to have our dreams shattered again. Let's look at the clocks for a moment. Yeah, let's just do it. 1, 2, and 3. I was thinking of using SPI 6 instead of SPI 5 to free up the pin. But if I want all ports to share the same clock for the SPI, we'll have 2 ports on one clock and 2 ports on the other clock, because we've already now established that they are different in many ways now. So but can we balance things properly still? Ay. This. Okay. Shall we hold on a second? God damn it. What can we do? What can we do here? We've got to try and balance this. Let's just disable that for now. I'm just going to say 2. Let's look at Tim 2 again. So Tim 2's got everything. Tim 5 can't have everything. I'm just going to turn off these two channels now. So TIM2 has channels 1 and 2. Yeah, at least then they're all equivalent, and these two are still equivalent, and these two are still equivalent, right? So we've got 2 and 23. And 5 and 24. And let me go back to the table of timers. I'm struggling with this now. This is shocking. Table of timers. Let's have a look at 13 and 14. (13 and 14). Okay, so they don't have an encoder, but it's fine because one of these didn't have an encoder anyway. So perhaps we reserve the two 32-bit timers. So let me take this out of here, just plop that there a second. And let's see if we can do TIM13 and TIM14. Oops. Which, no encoder, 16-bit. And let's just see if we can keep these for something else, because one of them has an encoder, which might be useful by itself. Let's look at 13 and 14. So, back to CubeMX. So let's turn off 5 and 24. Yeah, so 24 doesn't have that. It's just like, I just don't understand what goes through the heads of the people at ST. I don't understand, because they've got TIM23 and TIM24, right? And you need 2 GPIO pins to run an encoder, right? The only channels that you can use for the encoder interface, according to this, are ones that are connected to TI-FP1 and TI-FP2, right? Which are channels 1 and 2, right? Channel 1 and channel 2, right? And then if you look at the LQFP144 at timer 23, you don't get it. Okay, so we can use an encoder on 23, but not on 24. So 23 we need to keep. Maybe you want an encoder on the front panel or something. This is a mapping struggle. This is. Hold on a second. So we're taking off 24, but 24 doesn't have an encoder that we can use. Great. Okay. Disaster. Let me get rid of all this. Here we go. Let's do this differently. Okay. So 1, 8, 3, and 4 are fine. So 2 and 5. Let's try doing this. No. No, Microsoft. No. Let's try doing this. And then these ones are all using 4 channels. So let's try exposing TIM2 and TIM3, which are encoder and 32-bit. Well, you already found that we couldn't do that. Nuts. Nuts. Oh my God. It's a disaster. Hold on. 14, 16, 17. These have only got 2 channels on each of these. But they've only got 1 capture compare channel, so that's no good. TIM15 is randomly special by itself. With no DMA, and this one's got DMA. This is a just disaster. It's a disaster. On the LQFP 144. There's no good way of doing this with the LQFP 144 is what I'm deciding. I don't like it. I don't like it. Rename. LQ. Let's try again. With the LQFP 176. Okay. Because it's madness. So, CubeMX. We're going to save this. We're going to come back to our file. We're going to open the other one again. Oh, that's supposed to be 176. No. No. Stop doing that. Yeah. Timers. Connectivity. Ethernet. We had a problem with Ethernet on this one. We had a problem with Ethernet because it conflicted with TIM5. So we go back to TIM5 and just turn everything off for a minute. We'll come back to Ethernet. Turn on Ethernet. RMII. Okay. So we've got Ethernet, we've got that, we've got that. We've got SPIs that we want. And now we're back in timer land. So 23 and 24, we can have all 4 pins on those, which is good. And TIM2, but we can't have these pins. Okay. So, back to the spreadsheet. So if we have TIM23 and TIM24 here, and how about we have TIM1 and TIM8? With an encoder. Let's try that. TIM1. TIM8. Okay. Now we've got TIM2, TIM3 and 4. Now these timers were the same, right? And we've got 2 other ones that are the same. So if we have TIM3, oops, TIM3 and TIM4 on this one. And TIM3 was 16-bit, all right? Yeah, TIM1's 16-bit. Maybe we do this here. Yeah, there's... Because these are 32-bit, right? Oh dear, that was not right. Okay, yeah. So we've got 16-bit with encoder, 4-channel. Good. At least we have some symmetry there. You know, these are advanced control timers, and these are not. Now, the problem is, TIM5, it's got 1 and 4. So let's turn on 1 and 4. Let's put features. Let's do this way. So Tim 5 is channels, well, it's 32-bit, but you can't use the encoder on it. So channels 1 and 4. Tim 2 what if that's 4 channel? What if we switched one of these channels, one of the timers over from here to here? Wait, that's a 32-bit. This is why my brain is struggling here. Let's move that to here. Can we do this? Is it possible? Oh, balls. Oh my god. Okay, so Tim 2's got an encoder on it. Tim 5, you can't have the encoder because it conflicts with Ethernet still, even on this. Ah, it's a disaster. I've done it again. Like April Fools. Oh dear. No. What can we do? How can we do this better? This is such a faff. 23 and 24. We've got all 4 channels here. Let's keep that like that. Okay. So how about let's not use Tim 2 and 5. So we've got 3 and 4. Let's turn on some channels. Right. Okay. So can we turn on this? We should be able to. Okay. Tim 6 and 7 are special. Let's look at those other ones. Which ones was it? It was capture compare channels. No, see, that's no good. But they are the same. No capture compare channels. really annoying that I can't use 4 identical channels for this. Really annoying. Is there really no way to do it? TIM5. Conflicts with Ethernet. This is really annoying. Let me just put those there for a moment like this. We'll do it this way. TIM3 and TIM4. Let me just check that again. These do have that. And they are that. You know. Keep those the same. Okay, so I think this is probably the best solution here. Yeah, so TIM2 has got all the channels available. TIM5 only has 1 and 4 available. So if we go to TIM2 and sacrifice 2 channels, two and 5. So we've got 1, 4. Do we have a timer that's free that has a spare encoder? So I don't think we do at this point. Because 2, 3, 4, and 5. 2, 3, 4, and 5 have the encoders, but we can't use all the channels. Can we keep these for something else and just use another timer here? 2 timers. So let's ignore those. So we need 2 basic timers. Let's get 2 basic timers. No capture compare. So if we have tin 13, 14 perhaps. Let's have a look at those 2. Only one channel. Only one channel. 15 has 2 channels, but it's special for DMA purposes. These don't have output pins. Oh. Yeah. I'm also thinking of the other peripherals that need to go on the board itself. Let me add that to this list. It's just a mess. It's just a mess. 12 is different to 15. 2 capture compare channels, 2 capture compare channels, but it doesn't do DMA. I just want 2 sockets that are the same. What if what if we keep these for other things that I've got in mind, right? Put the 2 32-bit timers on this, and then use TIM 12 and 15. Let's see if we can do this. 12 and 15. Okay. Right. Then we've got other use. And we need to try this again with the LQFP144 in a minute, and we'll see if we can do the same thing. Because what I'm thinking, because this was possible, 23 and 24, right? 23 and 24. Yeah. That was possible to get those outputs. and this is actually working out quite nicely there. Okay. But did they just spread the pins out everywhere? Okay, that's actually not terrible. Okay, I'm going to go with this for now. That's not entirely unreasonable. So we also need PWM output for the other things that we mentioned earlier. So if you remember from the schematic from earlier, we had these 6 PWM output. Well, ideally we want 6 PWM output controlled things. And then there were 2 more PWM controlled things over here, and potentially 2 more PWM controlled things over here. Right. So here we've got 12, right? No, 10. We've got 10 outputs here, potentially. Yeah. 10's a funny number in terms of timers. But I don't think all of these actually need to be PWM controlled, because some were just on-offs, and some of the other ones ideally could be PWM controlled. But I think we need 8 PWM controlled outputs. So, given our mapping that we've got here, we've now got, let's have a look at the little diagram again. Where is it? We've now got the first 2 ports with encoder and 4 channels, and then 2 channels of another timer. So they're the same. And then this one has also got 6 timer channels, the same as the first one had 6 timer channels. But the second port only has 32-bit, only has 16-bit timers, whereas the first port, being more special, has all of the fancy advanced controller timers and 32-bit timers. So that kind of makes sense for like more special ports. So that's okay. We've got, do we have our SPIs on? Right, we've got SPI 2, 3, 4 and 5 turned on, which is good. Right. Oops. There we go. That leaves us with 4 channels on TIM 23 and 24 for the PWM output controlled ports that are going to be on the board itself. So I think we've got the timers as good as they can be. That was quite a mission, that was. Oh my god. Okay, let's see if we can flesh out a bit more of this pin mapping and peripheral to pin mapping. So we've got PWM controlled outputs. So we've got 8x PWM controlled outputs, which is good. And technically, we can magic up some PWM controlled outputs from thin air by using either a DMA stream, which driven by a timer, which drives the output data register of a GPIO port. So the idea there is you have a timer, one of the ones that we're not currently using, which do have DMA access, such as, come back list of timers, TIM 15, 16 or 17 for instance, because these have got DMA request generation, right? So you can use these timers to drive the bit set reset registers or GPIO output data registers of a GPIO port to get 16 more PWM outputs driven by DMA. That would work. Okay, so yeah, that would work. All right, let's go back to QMX and the list of requirements. Okay. Expansion connectors. This is what we're sort of looking at here. We need the USB on each thing, but that doesn't come from the MCU, so we'll ignore that. Ideally, we wanted one 32-bit timer per socket, but that wasn't possible. So, eh. But we do have the encoder support, so we've got that done. So we need UARTs and I2C. So let's do that. So we don't need a different I2C bus per port, but we do need an I2C which is connected to every port. The idea behind that is that you plug a card in and it can have a device on it, maybe a memory chip for instance, which has got a different address on it, and then you can look at the little memory chip to find out what is on the card so that it can auto detect it. You know, maybe we do that. Maybe you don't even need to do that, but you could do that. Or maybe there's some kind of sensor on there, or bus, or who knows what. But I2C we need. So let's just turn on I2C 1 for now. There's nothing particularly special about the I2Cs, except for the pins that they use. So PB6 and 7 have lots of signals on them. So dedicating I2C 1 on these pins that are used by lots of things is not necessarily the best idea. Bear with me a moment, my doorbell is ringing. Oi! All right, where was I? Sorry for the interruption. Okay. So, pin 6 and 7 are quite useful. So let's not use pin 6 and 7 for I2C. Let's use some other pins or other interface which uses some other pins which aren't as useful. Well, yeah. But doing that has moved TIM23 out from these pins, and I kind of don't want to do that either. So let's put those back where they were. Let's pin those signals where they are. Yeah, I need to go around this and have a look and make sure everything is sane. So let's try using I2C4, which is on PB6 and PF19 it's picked, but again we don't want to use this. So we've got PB8, which has got memory card, TIM16, TIM4. I don't really want to use the PB8. Is it available somewhere else? PB6. Oh yeah, it's available down here. Yeah, and that upsets the nice routing that we're going to have if we were to do that. So we don't really like using that either. Yeah. PA8 is a very special pin which we definitely don't want to be using for I2C, because PA8 has got the MCO output on it. Let's see if this is available somewhere else. Oh, it is. Okay. So if we move SPI to NSS to PB9, that frees up PB4 for SPI3, MISO, which then frees up PC11 for the I2C, which then frees up PA8 and keeps the I2C and the STA next to each other. So that's probably not entirely sucky. Let's see if we can rearrange some of these. TIM1 CH3 should probably be up here. Let's keep those next to each other. Then we've got TIM8. Let's keep those next to each other. Pin these. Oh, picked the wrong one then. There we go. Right, where's SPI3 MISO disappeared to? Look there, all the SPI pins are everywhere. Look at this. Madness. Madness. TIM2 channel 4 is sat there by itself for some unknown reason. Oh, it's because is that one of the channels that we're using channels 1 and 2 of? Yes. So so we're using 1 and 4 of these ones. Nightmare. And then oh my god. It's not easy doing this. You want to get your pin mappings good for your software and for your design. I don't like my position of my SPI2 pins. Like, what's up here? Like, we've got SPI, two of the pins of SPI4 up here, one pin of SPI2 up here. And then we've got some Ethernet down here. Let's move that. Let's move these Ethernet ones up here. These don't have any alternate pins. Neither does this one. The Ethernet pins are everywhere. This is crazy. And this doesn't either. It's nuts. Nuts, I tell you. And if I wanted to use SPI6, they'd all be up there. And then I don't know. DIM2 channel 4. What a mess. You just want adjacent pins to make your life easier. But no. No, ST have to do some weird stuff. Oh my god. The SPI pins are everywhere. SPI3. We've got the cable select all the way over here. And all the rest of the things are up there. I'm going to move that out of the way. We've not even thought about the ADC inputs yet. Oh, dearie me. We've got a random Ethernet pin over here. I'm going to move it up to one of these two. I might move it later. But I don't like it being down here. We've got SPI2 clock floating around down here. Where's the Mossy and the Miso for SPI2? They're over here. Can we move these two out of the way? What is this? DIM12. No, they have no alternate function mappings. Great. All right. Let's leave like that as it is for the moment. I can tidy this up a little bit more off stream. Let's add the rest of the peripherals that we need. So we've got I2C. We can put the I2C on each of the buses. So it's fine. On each of the expansion ports. So now let's go to UARTs. So we need a UART on each port. Now, there's UARTs and there's USRs. So some are more special than others. So let's go with the second-class citizens first, which are the UARTs. And let's see if we can turn on some UARTs. UART 4, 5. Seven and 8. Okay. So we've got that. We need the USB to the main system itself, and it looks like we've got a problem with this now, which is not ideal. Oh, that's interesting. Well, let's turn off UART 5. Probably should have turned the USB on first. A USB's over here. So we've got UART 4 and TIM 1 stealing the pins. Let's have a look at TIM 1 channel 3 and 4. Uh-huh. Uh-huh. Oh my gosh. What a disaster. And these don't have alternate pins. It's just chasing the rabbit around. It's like, you got this pin, but you can't move this pin, and then that pin can't move. Just I don't want a GPIO mux. GPIO mux. So let's go back to the data sheet for a moment and just double check to see where the USB pins are connected to. Yeah. Come on, searchy, searchy. Wait, what? The A11. Oh, it's called OTG. I kind of really want to be using those pins because that's where the bootloader is. We're looking for the DM and D+ signals, but I think they're only available on 2 pins. VBus, ID, DM and DP. They're only on 11 and 12, which is what I expected. Yeah, fine. So we have to use those 2 pins if we want USB. Do we want USB? We need USB because the microcontroller's got to connect to a USB hub. Well, that's a problem then. We can move that one. This one is more of a problem. PE14. We can move it over there, but then we can't use TIM15. This TIM5 is just a nightmare. It's just a disaster. Just going to turn this off for a moment. Yeah. Breaks TIM5. Got SPI3 over here. Where's the rest of the SPI3 pins? Miso clock. Just the pins are everywhere. It's just a nightmare. What's it doing down there? We broke Tim 5 though. Tim 5 was being used here. So what can we do? Maybe we can try moving some other channel around. So that conflicts with Ethernet, so we can't do that. That conflicts with Ethernet, so we can't do that. And this conflicts with Tim 15. Okay, so we've got Tim 15. Tim 15 was being used here. So if we can put something else there, so we've got Tim 12 and 15. Let's go back to the list of timers in the datasheet. Tim 15 was just a simple 2 PWM output. Now you see, there isn't another one. What if we don't use Tim 15? That gets us our 32-bit timers channels back on Tim 5. Let's turn off Tim 15. So now we can go back to Tim 5 and turn that on. Fine. So now we need a different solution for here. Ideally we want 2 more capture compare channels. So what I'm thinking now is, instead of doing Tim 12 over here, we put that there, and then we take one of these peripherals and split it across the other 2 ports. I hate it. I hate it. It's a disaster. It's a disaster. Let's look at the list of timers again. What if we didn't do that? Because I don't think it's a good idea. What if we did that and took this one here so that, you know, they're at least equal, right? But now we've got a problem because we don't have 8 PWM controlled outputs. But as I mentioned, we do have an FPGA, and we do have the option to use PnP to generate DMA requests, generate a DMA stream to control PWM generation. It's way more complicated than it should be. Way more complicated than it should be. But, you know, at least we have sanity on the GPIO, on the expansion sockets. The 8743, in answer to the question in the chat, Negvorsa, the 8743 has fewer timers than the H725. It doesn't have TIM23 and TIM24. So we wouldn't have the same capability with that. Honestly though, I mean, using the FPGA to drive some PWM outputs isn't the end of the world. Let's have a look at the other channels timers. So we've got let's have a look at the other ones that we're not using. 16's got 1 and 17's got 1, right? 13 and 14 have got 1. So we do have 4 more timer channels for 4 more pins. And I'm kind of okay with dedicating these to this purpose right now. So let's do that. We're going to reserve this for later. We can use TIM15 to do this, but I don't know whether we should. I mean, let's do it. So TIM 13 and 14. Let's PWM generation. Yeah. TIM 14. $16. And 17. All right. It seems a waste of timers to do that, but what else are we going to do with them? So we've got 6. Let's go back to Tim 12 for a second, because Tim 12's only got 2. Yeah. So these are normally used for driving audio, Tim 6 and 7. So we've still got 2 time channels free. Tim 15 we've got for that. We need 1. I kind of want to check to see what options there are in Embassy with regards to how it drives the time. Because there's only certain timers that you can use for it, I think. Yeah. Where is it? Yeah, here we are. Let's just check to see which timers can be used to generate the time for Embassy. Oh. Because we need 1 for that. Which is important to remember. What? So that's what I thought. See, what's missing on this list is Tim 6 and Tim 7. All right, here goes Tim 5 and then Tim 8. Nuts. So, whilst we do have Tim 6 and Tim 7 free, we can't use those for Embassy. So that's a bit of a problem. So we've only got Tim 15 left out of all the timers that we want to generate the internal clock for Embassy, because it needs it for its like async executor. Honestly, I just don't like dedicating this many timers to just PWM outputs. It's just madness. I think we can do better. I think the solution is indeed to use Tim 15 for generating a DMA stream. Let's just say 16 PWM controlled outputs on this, done, right? And then all the other timers are free, and I can do whatever else I want with them and need with them. And it complicates driving PWM outputs, sure, because we've now got to create a DMA stream and use a DMA channel to do PWM outputs. But we can change each output's frequency. Basically, the idea is you have a DMA stream and it has well, let's think about it for a moment. Paint. We're just going to use paint. We're going to fill that, resize it. I suppose the idea is that you go, time goes this way, and you've got, like, say, a byte of data, right? And you can have an on and an on and a on and then on the third channel on, maybe this one comes on, you know, and then you've got off You get the idea, right? And then each one of these bytes makes up the DMA stream, and each bit of the DMA stream is used to control the output data register, such that on port 1, I'll just draw 4 in here for now, right? So this would then be, let's use a different color. We'll use, it's high, it's still high, and then on this one it'll go low, and then this one is high on the, oh, I did that wrong. Hold on, let me do that better. No, it was right. It goes high and then goes low here, right? And then this second one is high here and it goes low, right? This third one comes on here and goes off. So it goes on, it comes on, it goes off. And then this fourth one is like that, and so on. So you can generate your output signals using a DMA stream. And then, depending on which pins you use for the DMA stream, there's a mapping in your DMA stream which maps to the output bit registers. So this is either ODR, or you have a double stream and it does it in burst mode, where you use bit set reset. If you're looking at the data sheets, the reference manual rather, if you look at the GPIO peripheral, where are we? This, in your list of registers, yeah, here we go. You basically configure all your pins how you want them, and if they're in output mode, then a bit that's written to the ODR register, this one, this register, when you write a bit to this, you can control 16 pins on the same GPIO port. If you're using your DMA stream in burst mode, you can write, no, you need 2 DMA streams for it, I think. Well, you might need, there's ways of doing it. You might need 1 DMA stream. I think you need 1 DMA stream per GPIO port. But the timer can advance 2 DMA streams at the same time, if I'm remembering rightly. So, how does that affect us? So what we need to find to drive our, where is it? To drive our 16 PWM controlled outputs via a DMA stream, ideally we want 16 consecutive pins somewhere around the edge of this MCU, which is unlikely at this point. But these ones over here are looking quite good. There's at least 8. Wait, 2, 3, 4, 5, 6, 7, 8. There is indeed 8. PG, wait, 7 there, is there? What about the other PG ones? Well, PG 1's unused and PG 0's unused. Oh, I think we're good. And then we don't need to use 8, so we've got that. What about PG 14, 15, 10, 9? There you go. So that's our 16 pins, PG. So let's allocate them to PWM. Let's see what else is on these pins. You want 9, that's fine. You want 9. Maybe we don't use those ones. You want 6. Ooh, we've got can. Okay, we've probably got a whole bunch of pins on port G. Up to GPIO-G. And then one of the timer needs to be used for embassy. But it can't use 6 and 7. So it had to use 12, 13, 16, 17, right? Oh, not 13, 12, and it doesn't have 16 or 17 either. Okay, well, that's our answer then. It's going to use TIM 12. It might just be that it hasn't been added, or it might just be some capability that it needs from the timer. Let's have a look. What did we say? 13, 14, and 16, 17. I don't know why. I might have to ask and find out why. Kind of surprising. Let's look at the data sheet. I mean, 13, 14, 16, 17. I mean, it seems like you should be able to use those. Is it like an interrupt thing that it doesn't have? I'm a bit confused now. How strange. Might have to dig into that. Now look. It uses TIM 12. TIM 12 is a general purpose timer. TIM 12 is different from TIM 13 and 14. Oh, okay, fine. Interrupt signals. I mean, it's not much different. What doesn't it have? We don't care about edge filtering for a timer, for like system time. No, don't need that. So it's not that. What is it then? No, we don't need any gating or anything like that. I don't know, it just feels like they've just not added it. Yeah, how strange. Let's ask. Why not? Is there any reason why TIM 13, 14, 16, 17 on an 875 can't be used for time source? Let's see. We shall find out. Let's find out. I shall keep an eye on the chat. Let's move this down here a little bit. There we go. Don't have two capture compare channels is the answer. Indeed they do not. So Tim 12 has two capture compare channels, but Tim 13 and 14 do not. Huh. Learning. So you could get very unstuck if you're doing your pin layout and you didn't know about what your software was able to do when you're allocating your peripherals. So these hardware designers, they go, yeah, we'll just allocate all these pins to this, and then someone has to come along and write some software for it, and they go, nah. Yeah. Okay. Back to the requirements. Let's see. Done. Mostly done. We need that second NSS output. There's a comparator on these ones. Trying to find some unused pins. I think these ones look good. We need some ADC inputs at some point. Okay, let's allocate these to this output. Oh. We can move these around as we need, but best we don't forget them. Okay, so we've done that. I think we did the UARTs, didn't we? We've got all the UARTs. No, we don't. We had to turn one off. Can we turn UART 5 back on? Okay. So we've got 4, 5, 7, and 9. Four, 5, 7, and 9. No, 7 and 8. We can rearrange those as we see fit. Some UARTs have DMA streams and some don't. Let's have a quick look to see what DMA channels and so on are used for them to make sure they're all on the same one if we wanted DMA. So DMA mux. This. So DMA 1, and then what was our list of ports? UARTs again. We've got 4, 5, 7, and 8 currently. So four, 5, 7, and 8. Okay, this is good. Okay, fine. Okay. Let me go back to my list of SPI ports. What are we? 2, 3, 4, and 5. I've got that wrong here. Okay. Yeah. So in the chat, that is a base requirement with regards to that timer stuff. So we have the answer from the man. He's Mr. Embassy. Very active in the community. I don't know how he gets anything done. He responds very quickly. It's very good. I'm always too focused at doing stuff, doing random things, rather than looking at chats and things all day long. Never get anything done if I did that. All right. Can we or can't we? I mean, I didn't mention can in this, but let's just done. That might not be done. We're on this line here. Stepper motors. 2 sockets need that. Now, the point of using, I think we've got this covered already. But the point of using the timers is so that we can drive the stepper motors. So we can use TIM 1 and TIM 8. And we've got loads of channels here to do it in the hardware. So each one needs a step and a direction. So if you've got one timer on port 1, it can do 2 motor outputs, step direction, step direction, step direction, and so on. Now, I think we need more UARTs. We need more UARTs. Because port 1 and 2, if they're doing 2 motors each, they need 2 UARTs each as well to get feedback from the stepper motor drivers. Because the stepper motor drivers have UART interfaces. We need to have a quick look at like a commonly used stepper motor driver and just check how they're wired. Let's move these to here. And now we don't have any UARTs on this port, so we need to find some UARTs. Well, we've still got some. I kind of don't want to use UART 2 yet. Let's have a look at using UART 3, 1 and 3. 1's a bit special as well because it's also connected to pins that can be used for the bootloader. So let's avoid the pins that we can use for the bootloader for the UARTs that are on the second port. So let's try and use 2 and 6. No, I said I wanted to keep 2 and 2 for something else. Let's use 6 and 10 then. Okay. We've still got plenty of pins free on port G. Okay. So 6 and 10. You know, and this isn't all fixed in stone. UART 6 and UART 10. Okay, let's have a look at a datasheet for a stepper motor driver. Who can remember the names of them? No. Let's look at Big Tree Tech's website again. Again, no affiliation here whatsoever, but they do have a list of stepper motor drivers. Here they are. So the 516 though is the good one, it's the fancy one. But I think these 2209s, yeah. Oh, what did I type there? No. What? It was that, wasn't it? I'm going mad. I can't find the thing now. Is it TMC 2209? Oh, let's just go LCSC. TMC 2209. Here we go. This. All right. So these ones are popular. Let's just have a look at what you need for IOs on one of these. So UART interface, MCU interface rather, step and direction. That's basically what you need. And then you've got some configuration-y stuff. Then you've got one pin which is like a unidirection, bidirectional UART. Programmable diagnostic outputs, diag and index. So you get feedback from the thing when it's done its stuff, and then you might have an interrupt on a diag pin. Okay. And let's just compare that with the TMC 5160. Which is the fancy one. It did say sewing machines there. Like a bit of sewing every now and again. It's quite therapeutic. Okay, so this has got an SPI interface, so we don't need the UART. And then it's got two diagnostic pins. So we need step direction UART, diag interrupt, or we need SPI, interrupt. So we need 6 pins regardless of which one we're doing. So we need those extra inputs. The diag and the index pins is what we need. Or we need diag 1 and 0. So we need 2 extra pins per fancy port. And these pins need to have interrupts on them. Oh yeah. Okay. So, and before I forget, we're going to need some oscillators. And maybe we want a real-time clock on it. Where's the debug? Oh, is it down here now? Yeah, it's down here now, debug. And we definitely want serial wire debugging. It'd be nice to have trace on here as well. Yeah, there it is. SPI3. And that conflicts with the I2C. Yeah. Okay, we might have to use a different I2C port. Let's try using I2C4. And that way we can turn on trace. There we go. We'll do that. Not too fussed about the I2C. Now I2C1. Where's the other I2C pin gone? I2C4. Huh. What's it doing all the way down there? PF15. Honestly. Keep that there. Fine. We are getting there with all this. We are getting there. Look, we've used many of these pins, but we were trying to get those additional pins for the diag. We're going to run out of pins, aren't we? Look. Canned peripherals. Oh my god, memory. It is quite amazing how quickly the pins disappear when you're doing something like this. You're like, 176 pins, that's hundreds. It is almost hundreds. These pins up here look good. 1, 2, 3, 4. We need 4 for the first one. Diagonal into, yeah, okay. What's on these pins? Memory controller, UART5. We're using UART5 somewhere else already, aren't we? So we don't care about UART5. Octospim, UART2. Let me turn on UART2 before we get fancy. Because in our requirements list, the MCU done. Because in our requirements list, what was I looking at? I got completely sidetracked by what I was looking at. Yeah, that was it. UART2. Because in our requirements list, we've got the head on the pick and place machine, right? And it needs to have some communication to it. So I was thinking of using perhaps RS422 for that, and or maybe with flow control. So let's turn on UART and reserve it for that. Let's turn that on and make it asynchronous with RTS CTS. Oh wait, hold on, disable. But we can turn this on here, right? What did that do? What does this do? I haven't actually used this bit before. Oh, it uses DE. What pins does it use? Oh, it's got device. Oh, I see. Right. We don't need that. We don't need that because it's RS422. It's only point to point as opposed to multi-point. So the RS485 is where you have multiple devices connected to the same bus, like you do with I2C, and one of them needs to transmit at a time. And this hardware flow control enable bit is to enable the differential driver to drive the bus signals when it's enabled. So we don't want that, but we do want RTS CTS. And those 4 pins are all next to each other happily up there, which is good. But we still need 6 pins that aren't on port G. Yeah, okay, let's update the little spreadsheet. No, not that one, this one. UART2 with RTS CTS for head comms. The other thing we've got for the head is CAN bus. I don't know whether we want to use CAN bus. CAN bus is a bit funky. But let's see if we can enable these. Oh look, we can actually enable 3 different ones, so that's good. Okay, let's actually try enabling all 3 of them and see where the pins land up. Oh, that was interesting. Not entirely happy with where all the SPI things are, but there we are. Okay, we've got one for the head if we need it, and then one for other stuff, expansion if we need that. Now, okay, I think we've got that. That's good. Okay, FD CAN 1 for head comms, and then FD CAN 2 for expansion header, not a peripheral port header. I mean, wait a second. Yes. That actually, yes, that's what we want, isn't it? So we want FD CAN for expansion ports. Yeah, and because it's a bus, it can be on the peripheral thing as well. I think that'll work. So let's go back to our Krita thing. So we've got where is it? I struggle with this program. Oh, do I have to select it? Ah, there we go. Select a layer first. I really wish this was a bit bigger. I mean, like, I can make it bigger there, but then it's massive on the thing. Yeah. And why is it using this grey colour? Can we make it in white? Okay, there we go. Let's see. So I2C, come on, can. I mean 2x diag in pins. We haven't got that yet. We can, and then we've got 2x URs. Ports 1 and 2. I'll come back and update this. Come on, that's it. Can you scale this without changing the text size? Like, I don't know. Pixels percent. Let's say 25%. Does it? Oh, there we go. That's good. So now when I'm editing it, I can read it still. Everything's fine. And then we'll come back and update the list for the other one, but I'm concentrating on these two down here. We still need to do that. FDCAD, we've got that, we've got that, we've got this. We've got SPI, plus 2 signals. Let me save this file. This one, design, port diagram and signals. Okay, that's kind of what we're trying to work towards here. Okay, so going back to this, we've got a can, we've got our I2C. Did I have I2C on that list? Yes. We need emergency stop still yet. We've got analog inputs still. Oh my god. Let's do the analog input pins and come back to those diag pins. We're running out. Hold on. Let's have a look. We've got ADC1, not port G. Where did Tim1CH4 go? Oh, it's there. Yeah, we had to move it, didn't we? Were these Tim1 available somewhere else? Hold on. Yes. Yes. Okay, let's use these pins down here for Tim1. That frees up 9 and 10 for a UART. That's what I'm thinking about that. Add that to the list. I don't know. Probably going to need to talk to the FPGA at some point. Let's do that. Speaking of the FPGA, I don't know. Maybe we need to use SPI and treat the FPGA as some device with like peripheral registers and things like this. So perhaps we should turn on SPI 6 for that, because we can clock it at whatever speed we like. Let's see what we can do here. Half duplex. Oh no. Let's search for SPI 6. So if we got half duplex, that means we need the meso pin, which is currently used by these things. Tim3 channel 1. Okay, let's not use FDCAM1, but let's use FDCAM3 instead. All right. Let's turn on that, but we still need SPI 6 underscore meso. Tim1CH3 is where we came to. CH3? Tim1CH1, sorry. Tim3. CH1. Oh, what a pain. What are we using Tim17 for? Wait, what? We're not using Tim17. Oh, I should turn that off. Oh yeah, I forgot to turn these off. Okay. Let's turn off TIM17 then. Okay. So now we can move. We can move that, and everything should be fine. We were trying to do SPI 6 in full duplex. There we go. All right. We've still got those other timers turned on, so we've got one spare timer for doing things with. TIM15 needs to be used, so let's go output compare no output, because it's used internally, but we need to have it on so we don't accidentally use it for something else. But we still need, we've not got enough bins. It's not enough bins. my PG6s are disappearing. My BGs, look, my output pins. I need 0, 1, yeah. 2, 3, 4, 5, 6. We've got 8. We've got 8. But all these ones up here just disappeared. We've got 15. Yeah. Okay. Right, I'm going to reserve these now. GPU output. And this is going to be DMA PWM1. I keep doing that. Every time. I always think you right click it to do it, but I don't know why. Why don't they have this enter user label signal pinning and pin stacking on this? I don't know. 4. No, that was supposed to be 3. Was it? No, it wasn't. Oh, I suppose I started at 1 and it's 0, so it's 1 higher, so everything's fine. So this is 5. 6. Every time. And 7. Right, so we've got no. 8. There we go. So that's our 8 outputs there. Okay. Okay. All right, it's looking pretty thin. Now, you are 8. Well, we still need ADC inputs. No ADC, no ADC, right. This one's good for an interrupt. I'm going to reserve this for emergency stop. We've not even got to status LEDs yet. Oh my god. Diag pins. We still need diag pins. Okay, so I think what we need to do is, because there aren't enough pins, right? We've got a table here, right? And we've got these timers, and we've got 4 channels, and then we've got 2 channels. Now, I think what we probably need to do is make these pins that are currently connected to the timer channels also be either used as timer channels or the diag pins. Because if you're driving a stepper motor on one of the ports, you use 4 channels for 2 stepper motors, right? If you're using step and direction. And then you've got the UART, and then you've got 2 pins. So we need 2 extra pins per port if we were doing that. But we've also got our SPI port pins, which has got 4 pins as well. So probably what needs to happen is either the UART pins get used as the interrupt signal pins when using an SPI based stepper driver, and that's 4 pins there for that, because there's 2 UARTs per port, right? So that gives us the 4 pins, which is fine. And then if we were using 2 UARTs, we use the SPI pins, and we still keep the timers free. So I think we've got enough. SPI or diag 01, right? Because you never need UARTs and the SPIs at the same time, because it depends on the stepper motor driver interface that you're using. But we need to be a little bit careful, because you get different interrupts depending on the pins that are used. So ideally, we need to arrange these pins, all these pins, so that the XT interrupts are sane. That is tricky. So if we look at our SPI2 pins, we need to make a list. Right. The way that the interrupts are allocated between the peripherals changes. Let's have a look. Not that data sheet. This data sheet. Interrupts. NVIC thingy. this. Here we go. Right. So we've got these various different interrupts. And the way that it works is if you've got GPIO A0, it uses XT0. If you've got A3, it uses XT3. But the problem is that there aren't one interrupt per port pin, right? XT5 to 9 use the same interrupt, and XT10 to 15 use the same interrupt. So the interrupt signals are XT5 to 9, well, let's just say 9, 5, and XT10, 15, and then you've got XT4, 3, 2, 1, 0. Okay. So what we've got to do is balance out the XT and UART pins and ports across the interrupts. So here we've got SPI 2 and UART 4 and 5, and we've got the pins. So this PB9 corresponds to this interrupt. PB10 corresponds to this interrupt, right? So we need to somehow magically balance all these across. XT2, XT3, UART, and this is before I've balanced all the pins as well, because I haven't finalised that yet. So UART 4 is currently on. So we may need to move the UARTs around to balance things up properly. UART 4, here we go. So we've got PD0 and PD1. And then the other UART was, where is it? Where's my list? UART 5, PC12 and PD2. So here we can see that that interrupt is already used. So PC2 doesn't make a good candidate. Let's make this red. Oh, hold on. That wasn't supposed to be there. That was supposed to be here. But wait a second. Everything's fine. Because you either use these or you use these. So we're okay still, because as long as these don't clash and these don't clash, we're okay. Yeah. So we've got SPI 3, UART 7 and 8. So let's look for that. SPI 3, A4, BB2, BC10, BC11. So that one's that one, that one's that one. Bad. No, it's different pins. Same interrupt with different pins on it. Okay. It's fine. And then I guess this is XD4 and XD2. And let me just put the emergency stop in here before I forget. And currently this is on PC 13. So we may consider moving the emergency stop to a different pin so it's got its own dedicated interrupt handler. PC 13 is, yeah. So ideally we want like a one that starts with 0. Like this one. PE0. We might move the emergency stop to PE0 or PE1 because you want a high level interrupt on an emergency stop so that it overrides everything else. Because, you know, safety. So UART 7, PE7, and PE8, and UART 8 is on PJ8 and PJ9. Yeah, we've got a problem there. Because these two clash. So, should we move UART 8 to port 1? So, we've got 8 and 9. We've got a 9 here. So that's no good. Should we move UART 7 to port 1? 7... not used. 8 not used. Okay, so let's move that around. So let's move UART 4 here. Take this up. Let me slap it here for a moment. Five and 7, and 4 and 8. There is some nice numbering going on there with odd numbers and even numbers. Let's see if this is okay. So we've got 1, 2. Yeah, we've got 0. It doesn't matter. But do they conflict? That's the thing. So 0, 1, 2, 4, 10, 11. They do not conflict. And 8 and 9. So this is actually 5, 9, right? Kind of okay. Okay. I'm kind of happy with that. You want 6 and 10. We could move one of these two to one of these if it works out better. So let's just map those out to see what they are at the moment. Let's do the same thing. You are so SPI 4, 5, 6, and 12. There we go. Okay. So this is XT4, 5, 9, 5, 9, and 10, 15. And this has UART 6 on it. And that is on EG 9 and 14. So that doesn't work. Oh wait, yes it does, sorry. It's the same interrupt, but the pins are okay. So 4, 5, 6, 9, 12, 14, so that's okay. So that's okay. Next port. So port 4, SPI 5, on PJ10, PJ11, PK0, PK1. So here we're on XD0, 1, 10, 15. I don't think there's going to be any way of using that low-level interrupt XT0 for the emergency stop. Not if there's too many things on using like GPA 0 on GPA pin 0, signal 0 on the ports. Okay. UART 10. We can look for alternatives, but not sure. Anyway, UART 10. PE 2 and 3. Oh, we're okay. 2 and 3. God, happy days. Happy days. Now, do any of these clash with each other? So they're all okay by themselves, but what if you want to use 2 ports? Right? That's a much harder task. So if you've got port 1, I guess this is why we've got an FPGA, really, isn't it? I suppose. I don't really want to route the signals through the FPGA. but we could if we really needed to. Anyway, let us continue. Let's see. Right. So you either use UART or you use SPI. So 0, 1, 2, 7, we've got 2 on 8, so those two clash here. And we can't swap out UART 6 here, or can we? E.g. 9 and 14. Maybe we can move UART 6 Yeah, there we go. Are we back? We're back. Maybe. Maybe? Yes, I think so. There you go, that should be fixed now. I don't know how long that went out for. I hate it when my mics die. Okay, well next time I remember to plug the cable in. Sweet. Okay, let's see. So we were looking up encoders and whether we could use the remaining 2 channels in the timer for use for driving step and direction in hardware, but it's not entirely clear whether you can or not, but it doesn't matter too much. Yeah. Yes, that's annoying that that sound died. Never mind. Never mind. So, but what we can do is use the pins in bit bash mode. So that's what we'll add in the notes. Why does it do that? Come on, Microsoft. There we go. And then this is maybe these 24. So, not ideal, but it'll do. All right. Don't need any pins for that. Communication interfaces. Let's just double check the communication interfaces. Well, we've got the Ethernet. We've got the Ethernet, haven't we? Yes. So. So we don't need any additional pins for that. Cool. Right. Digital inputs. We didn't need didn't need 6. We didn't need 6. We've got 4 digital inputs. Let's double check against the schematic. Here it's got 8, but on the board that I've got, there's a missing socket here, so we only need 4. Plus we've got the FPGA, so we can say, do we have digital inputs? Let's update this. Now, let's have a look. So the only pins that were used on my machine were 5, 6, 7, and 8. 5, 6, 7, and 8 are these ones. And they're used for these, as we can see here, 5, 6, 7, and 8. Yes, good. So we've got P2, 3, and 4. And PC13. Let's have a look in the data sheet for the F4. Alrighty. Hold on a second. Okay, let's have a look. Pin description. And then we were looking for what? I can't find the file. Not that. This. PC13. Let's look at that one first. It is 5-volt tolerant. Hold on a second then. So the digital inputs that we decided that we're going to use, which I've lost. There's one down here. There they are. Can't see them for looking. PJ8 and PJ9. Oh, that's handy. 5-volt tolerant, yay. So PA9 is as well, so that's okay. Digital in PE10 next. FTHA. Okay, that's cool. And then the last one, digital in 4. Is up here at the moment on PD7. And this is also 5-volt tolerant. So yes, we've got 5-volt tolerant input pins. Happy days. Done. Yeah. Let's see. Let's see. So the analog input pins. We've got some ADC inputs over here. now. So we've got PF 4, 5, 6 and 10. Four, yes. 5, yes. 6, yes. And 10, yes. Very good. Done. This is looking good. This doesn't require any MCU sockets, and MCU pins rather. On the pass-through connector, I'll come to that another day. Logic expansion. Would be nice. Might be nice to have more I2C, but let's go back to this a second, because we said we've got SPI 2, 3, 4 and 5 enabled for the I/O connectors, and then we've got SPI 6 that we can use for like on-boardy things, and that's got one CS pin. So we've got this spare pin over here. So let's make this another SPI pin. Or oh, and it's on XT0 as well, that's interesting. We can't use it. I'm just thinking that we might need an interrupt signal to go from the FPGA because normally you do. Sometimes you can say go away and do something, and then the device notifies you that you need to talk to it. We go back to the list of XD signals. Right. I reserved it, didn't I? I reserved it. I reserved it. This is good. So we've got this XT reserved 15. Here we go. Let's give it a label and go FPGA XT 15. Now I'm wondering whether we need a dedicated XT signal for the FPGA, but I don't think we can do it anyway. Okay, so we've still got PC0 free, which is good. So let's use this as SPI 6 CSS2 as our output. Yeah, let's try that. Not hardware driven, but that's okay. And I think we finally cracked the pin layout. Yeah. Yeah, huh? I think we've got most of the stuff that we need. Tell you what we don't have though. We don't have any way of driving the LED on the RJ45 connectors. But you know, come back to that. Yeah. Okay. Yeah. So let's say, because we've got, let me look at the search list for SPI for a second, see if I've got everything right. Yeah. One of the things that I wanted to do is like maybe add a Wi-Fi module to this, right? So if you've got an FPGA connected to the MCU, or you've got a Wi-Fi module connected to the MCU, then if the Wi-Fi module and the FPA are connected via SPI, then you need a slave select for each of them. But ideally you need an interrupt for each of them as well. So we've got an int for that, and we've got a CS for that. But you need one more interrupt. Yeah, that would be ideal. I mean, I've got these book-in ones. I don't really want to remove those. I suppose we've got this trace output. Yeah. I suppose we could use that. I know. I've got a better idea. Let's connect the LED, right, to the SWO pin. And then you either have SWO or you have an LED. That frees up the LED pin to be used as an interrupt pin. Except that it's on PG15, which is annoying. Because our other... Well, I suppose we could read the interrupt on 15 and then read the corresponding GPIO port to find out what device signaled us and then read it. Yeah, it's not ideal. Let's see if we can fix that. Let's see if we can fix that. So if we go SWO or LED. Right. But we haven't got any unused XT signals anyway, so we kind of like, sort of like we have to do that. Let's look at the list. So that doesn't clash with that, that doesn't clash with that, which is good. That clashes with that, but we don't care, and that doesn't clash with that. So emergency stop is using 13. So if 0 and 1 are used, then we can't use 0 and 1, right? If 2 is used, then we can't use that, right? So if we assume that 11 here is never used as an XD because it clashes anyway, right? That means we need to find a GPIO pin on GPIO 11. Okay. So, can we move something that's on a pin 11 somewhere? So here we've got that one, that's no good, can't move that easily. Pin 1, CH2, ooh. 1, 2, they're both on 11, we can't move those, I don't think. So we need to, what have we got on here? Nothing. Nothing. Okay, hold on. Look, here's one. Ooh. We could use that. What about any of those digital ins? Digital in freeze on 10. Where's my digital in 1? Hiding. Here it is. SPI1 Mossy. Doesn't really help. So we're looking for signals that are on 11 on another pin that we can move to like one of these pins or something. What else is on these? You are 8 again, but that doesn't help. PnP channel 1. That doesn't help. PJ11, SPI 5. Where's that? No, that doesn't help. Most non-trivial. I think we need to move this CSS pin. That's the only way of doing it. It's the only thing that we can move, isn't it? Can't move this. SPI3 miso maybe? No, because we've not got that. Can't move that. Can't move this stupid enable signal. No. The only thing for it is to move this. I suppose it's okay. You know. Kind of do want to, but it is a useful signal. You know, reading a GPIO data input register doesn't take too long, and it's not going to delay the interrupts much, but it does delay it. And it's just additional code that you don't really want. I like having all of these over here. I don't want to move them. I think this might be one of the times where we do solve it in software. So it assumes though that the device holds the signal high as opposed to just triggers it for a short amount of time. But if it's coming from the FPGA, we control that. If it comes from something else, we don't control that. So I'm going to use this. I'm going to keep PF15, PG15. Yeah. We're going to share that XD between the two SPI configured devices, and then we're going to check the GPIO. So there's a question. Negvorsa says, if a motor driver either uses SPI or UART but not both at the same time, can those interfaces share the same pins? No, because of ST's lack of GPIO mux. It would be ideal if there was 4 SPI pins which also had alternate functions as a UART port and then another UART port, but alas, that is not the case. Plus, you don't actually know that you're going to want one or the other of those things. There might be, you could envisage a peripheral that you could plug into this that wants both two UARTs and SPI on it, and is not a motor driver. All right. So with the layout that I've got at the moment, it allows us to do whatever we want with the ports. But if you were using a motor driver, then you don't use the UART for one of the motor drivers. You use the SPI instead, or vice versa. So flexibility, an unknown future, is what we're trying to do. So we're going to say this is Wi-Fi XT. So we've got two things on two signals that both trigger XT interrupts. I need to verify that this does work like this. I think the XT interrupt is raised when the GPIO signal changes, and then you read the XT interrupt registers, the XT peripherals, and the NBIC registers. Then you find out which interrupt is raised, and then the process is then in that interrupt handler to immediately read the GPIO register for both PG, for port G, and for port oh, what happened to that? Why did it? Oh, I see. Let me undo that. And for port F, so we read F and G GPIO levels, and then we look at pin 15 on both. Let me undo that. Let's double check to make sure that actually works like how I think it does. Because the fact that I changed it from one to the other and it moved the signal across leads me to believe that perhaps it doesn't work like that. I need to look. Yeah, the trigger selection. So it's an internal signal. Probably scrolled past it, but let's look at the GPIO ports. Kind of think it probably would be in here somewhere, but it just says if you want to select it, you can say source XT input mapping. So I want to say XT15. Maybe it's not a good idea to do it like this. Let's have a look at the GPO. I think this is a question I need to like do a bit of research on. This is a bit unknown. Don't know this. What boards am I going to do? This might be a question for an AI. Should we just try and ask the AI for this one? It might know. Let's have a look. Let me see if I can do a... Let's see. On an STM32H7 processor with 2 pins configured as GPI inputs. Both pins are end in the number 15, e.g. BF15 and PG15. Is it possible to use both pins to generate interrupts so that an interrupt handler is called when either pin goes high? Yeah. Ideally, the interrupt handler would then use the GPIO IDR register to determine the source of the interrupt. Let's see what it says. Yes. But shared by pin number, shall I know? Only one GPIO port can be connected to an XT interrupter at a time. Yeah, I mean the AI is sort of thinking what I'm thinking, so you can't map both. Sysconfig XDCR, this is it. Yeah, let's look at this. It's here, look. Sysconfig. XDCR here. Right, so that's a no. Damn it. Okay, back to CubeMX then. Okay, so we can't do that. So we're gonna have to move PD11. We can't do anything else. Okay, let's see what other things are on here then if we can't do that. Nothing useful. Nothing useful. UART3RX. UART3TX. Okay. We're not actually using UART3. Oh, that's interesting. What I was hoping was I could move UART3 over there and free up a pin up here, but no. That is not the case. Wait a second, hold on, I've just remembered something. I've just remembered something. Remind me to come back to the other timers in a minute. Let's call this XT11. And this is going to be Wi-Fi int. And this is going to be an output. And it's going to have this name. It's not ideal that that's up there, but it's probably not the end of the world, really. Because the ports are quite far apart, and it's only a cable select line, so it's not critical. Let me rename this better. Wi-Fi XT11. Okay, so I think that's good there. Now, going back to those timers. So if you remember, we've got, I've lost my list, this. So we've got timers. Now when we were looking at the timers, we've got TIM15 driving a DMA channel with no outputs, so that was fine. So let's just double check to see what I've got over here. TIM15 with no outputs, right? But I turned on those other timers, 13, 14, and 16. Oh, this is going to work out very nicely, I think. So we've got 13. It can generate PWM, and it can also do input capture. Haha. Okay, this is good. 14, same thing, and 16, same thing. This is excellent. What it means, we've got 3 pins I'd forgotten about, and in my list of requirements, I had PWM fan headers. Haha. This is good. With RPM feedback. So I suppose what we could do, right, is use some of those timers to do fan header reading, I suppose, but we still need to generate the PWM signal for the fan itself. So let's just say need FPA for PWM and RPM feedback at this point, because the other PWM controlled outputs were for other things currently. Let me look at my schematic again. So we've got vacuum and blow. Vacuum switches. These are ones I keep forgetting. Vacuum switches. Yeah, and that's the 8. So we don't have the PWM fan. We can't generate it. We could do like one. We could do one output with RPM feedback, or we could do 3 outputs. Let's go back to this. We've not got any pins free now. Yeah, we do have these 2 book-in ones, but yeah, they're not on the right pins. It'd be nice if there's some free pins on port G. That would mean moving UR6. Don't think we can do it. Don't think we can do it. Don't think we can do it. I think that's going to be as good as it's going to get. We don't have fan headers. We've got an FPGA though. Maybe that's the first thing we do with the FPGA. It seems like a pretty good use of an FPGA. Generating PWM output signals. So I suppose we need to ensure. Yeah. We need to ensure that there's 4 PWM circuits connected to the FPGA. Seems reasonable to me. Seems entirely reasonable. Then we've got a reason to actually program the FPGA. We didn't until now. That's the biggest overkill of an FPGA ever. Is to generate PWM signals. Still. Yeah, everything's fine. I think we've got everything. I mean, we've still got 3 timers with capture compare signals on them, which is good. I'm going to make a note. I don't have any current use for these timers, which was, what did we say? 13, 14, and 16. Each with capture compare. Here we go. Jump. Yeah. We can make blinky lights out of them. We can drive LED strips. No, you need a DMA stream for that, don't you? No. We can use the FPGA for that. Or we could just bit bash the pins. Who knows? What's my would be nice list? I do see headers, octaves, hype. Yeah. Yeah. I think. Well, you know. Well. Yeah, we can use the FPGA to drive the LED Ethernet port pins, LEDs. Yeah. It's like, what are we going to connect to this FPGA? Need to think about that. Why is it doing that? There we go. Thanks, Microsoft. Again. Let's have a look. I think we've got everything. I think we've actually finally got everything. Why is it not letting me reason? Stupid. I think we've got everything. We've got it. Obviously, you know, we need to make a schematic and verify all this and wire everything up. But this is what we've ended up with. That's what we've ended up with. Let's have a quick scan of this little peripheral list and see if we've missed anything stupid off. We've got oscillators, we've got debug. That's what you need to bring the chip up. I suppose we could turn this on, but we've got our timers, all the timers. We've got Ethernet, we've got 2 CANs, 1 I2C, 5 SPIs, 8 UARTs and USB. That's probably going to do it. That's probably going to do it. Yeah. Wow, this is a long session today, this is. So, I guess the next thing to do, not now, but what I'll start on next, is I suppose start making the schematic for this board now that we've identified how everything's going to be hooked up to the MCU, because that's the most important task before we do anything else, really. Let's just have a quick look to see whether we can use the BGA version of this or not. It doesn't really matter at this point, I don't think. But let's see if we can do it. I don't care about LQFPs. Oh, packages. Let's see what it comes up with. So basically it's searching for other MCUs that have got the same signals on the pins, or the same available signals. This will be interesting to see what it finds. With a bit of luck, it'll find the other 8725s, but it might not, because some of the pins on those are used for the SMPS and things like that. We shall see. I'm making my computer work today. Oh yeah, need food. I think we're going to be finishing up after this. We're going to see what it says. Come on, little window. Okay, so I suppose while we're waiting for that, yeah, there's lots of resources and design resources that I'm going to need to read up with regard to wiring up FPGAs, because I've never done one of those before. So that'll be interesting. But I'm kind of amazed that we needed every single one of the LQFP's pins, every single signal that was available. I mean, we've got 3 unused signals. Technically, we've got 3 unused signals, and that's it. But if I don't use those signals for anything in particular, then I'll use those signals to knock off the things that are on my would be nice list, which included 2 additional high current PWM controlled outputs. So 2 to 4 additional ones of these. So maybe I use 2 of the timers, 1 each for those for PWM output. That seems like a pretty decent use. Probably use 2 times 2 additional high current outputs. That seems fairly reasonable. And then that gives me 1 timer left on a pin. And it's useful having a timer on a pin, and then we can assign that to something as we decide. And maybe we put an LED on it too. Yeah. Wow, it's really slow. I don't know what it's doing. Alright, well, I'm not going to bore you guys waiting for this dialogue to complete, but we made excellent progress today. That was a lot of work. That was a lot of work. So yeah. So yeah, join me on the next stream. Hopefully there won't be any audio problems. I have to remember to plug the USB sockets of the mics in. Sorry about that. There's a gap. And if you enjoyed this, stick some comments in the chat. If you found any of it interesting, then yeah, great. So just remember, folks, how hard can it be? We'll find out on the next one. Catch you guys later. My OBS has died. Alright, catch you on the next one. See ya.